Was Mars simply a cold, rust-colored loner in the solar system, a barren desert that never knew the warmth of oceans and the song of life? Or had it once been something else entirely, a cradle, a workshop, a bright-fashioned city of minds now erased by time? The question arrives like a splinter under the skin of curiosity, small, insistent, and impossible to ignore. It sits at the center of so many other questions about who humanity is and what the universe allows. For some, it is a scientific puzzle. For others, a moral mirror. For almost everyone, a story waiting to be told. From the vantage of the present, Mars is more than a planet. It is a repository for human longing and dread, a canvas on which generations have painted hopes for neighbors, enemies, or ancestors. The magnetism of the red planet is partly practical. It is close enough to be reached, to be touched by human-made machines, and partly mythic, a bright ember in the night that has been watched since language. The way Mars fills the human imagination reveals as much about Earth's inhabitants as it does about the planet itself. In that sense, the question of whether Mars was once home to a civilization becomes less about proving a specific past and more about understanding a pattern of human thought that stretches across deep time. From the first moments when people lifted their eyes to the sky, Mars appeared different. Its slow, deliberate wanderings among the stars made it an anomaly. Ancient cultures read meaning into that anomaly, a god of war, a harbinger of season, an omen of harvest and drought. These early associations were emotions encoded in myth, reverence braided with fear. That pattern repeated and amplified through centuries. The more the tools for seeing improved, the richer and stranger Martian interpretations became. Telescopes, spectrographs, radio arrays, each new instrument translated Mars into a new kind of story. The 19th century brought a peculiar chapter in that ongoing conversation. When observers with telescopes began to sketch linear features and darker swaths, the world was fertile ground for speculation. Words like canals passed from observer to popular press and then into collective imagination. Canals implied intent. Canals implied engineering. The notion of a planet with constructed waterways became an idea capable of stirring practical fantasies, of trade, of diplomacy, of conquest, and metaphysical ones, that intelligence might be a cosmic constant, that loneliness might be not the rule but the exception. That hypothesis did not simply arise in laboratories, it thrived in parlors, cafes, and serialized fiction. The possibility that Mars might be home to built landscapes, to machinery that altered climate and carved valleys, ensured its place in newspapers and novels alike. It became, for a time, a mirror in which the anxieties and ambitions of human societies were reflected at planetary scale. The same era that imagined Martian canals also constructed imperial maps, planned megacities, and theorized about the engineering of nature, so it should not surprise that the stars were colonized by the same imagination. Yet scientific observation has a way of smoothing out romantic outlines. The first close-up glimpses of Mars in the 20th century began to reorder the popular story. The Mariner flybys and later orbital surveys presented a planet that was not lush with canals but pockmarked with craters, scarred by volcanoes, cut by valley networks that suggested water but in patterns unlike Earth's. The public reaction cycled through disappointment, recalibration, and new fascination. The idea of Mars as a readily habitable world gave way to the recognition of a world that had once contained environments more clement than it does now, environments that hinted at rivers, lakes, and perhaps shallow seas, and then a transition into cold, thin atmospheres and permanent frozen deserts. Those images introduced a new emotional tone toward Mars, a melancholic curiosity. The feeling was not simply that of a failed neighbor, but of a world that had suffered change, perhaps catastrophic, perhaps gradual, and that preserved in its scars an archive of processes. Ridges and deltas became sentences in a long planetary biography. Sedimentary layers read like pages crumpled by wind. In geological terms, the planet's prime habitability lay not in the present, but in a chapter many billions of years old. That temporal gap magnifies the mystery. Deep time is not intuitive. To imagine landscapes shifting across millions and billions of years is to confront human smallness. Yet this is where Mars becomes most compelling. It is a planet that shows in sheer visibility the consequences of climate and chemistry writ large. Where Earth has folded, subducted, and obliterated some of its oldest surfaces through plate tectonics, Mars preserves ancient terrains in a way that makes the passage of time legible. At the same time, that preservation is partial and deceptive. Wind-driven abrasion, cosmic bombardment, and volcanic resurfacing have rewritten many of Mars's pages. if there had been complex structures, monuments, or other marks of organized life. The persistence of those marks depends on material durability, burial, and the severity of planetary processes. Over a span of billions of years, even stone can be pulverized into dust. Organic molecules can disperse, oxidize, or bind into immobile forms. The archive is messy. Science has treated the proposition of a Martian civilization the way it treats other extraordinary claims, with methodological caution and a hierarchy of evidence. The presence of water in Mars's past changes the calculus. Liquid water is an ingredient for life as Earth knows it, and the signs that Mars once held stable bodies of water open a door, not a guarantee but an invitation. The discovery of past aqueous environments, of minerals that form in water, of organics tucked into ancient sediments. These are the sorts of clues that will be consistent with a biological past. They are not, by themselves, proof of intelligence. Intelligence leaves specific kinds of signatures, artifacts that resist the slow processes of planetary change. But the longer the timescale, the thinner those signatures become. This is where the conversation shifts from strict empirical cataloging to interpretive imagination. The speculative documentary mode lives in that transition between evidence and the stories humans tell to make sense of absence. To ask whether Mars could have harbored a civilization is to examine, in parallel, how humans assign meaning to loss. It is to ask what humanity values and fears when confronting the possibility of a vanished world. Would a species' entire cultural archive, its poetry, its politics, its inventions, leave any trace after a geological eon? On Earth, civilizations have been erased by erosion, by the slow creep of glaciation, by volcanic burial. The archaeological record is an accident of preservation and contingency. On Mars, where the environment moved from wet to dry and where wind and dust are relentless scribes, the odds are unfavorable for the survival of intricate relics. But the query does not rest solely on the likelihood of preservation. It also probes motive and consequence. Suppose a civilization existed and vanished. How would that alter humanity's sense of destiny? If Mars had been a cradle of minds that rose and fell, would that be a cautionary tale or a shared lineage? Would the knowledge of having been preceded expand empathy across time, or shrink human hubris? The speculative power of the question is not its provability, it is the ethical and existential space it opens. It invites the species on Earth to imagine its own vulnerability to planetary change and to grapple with the stewardship of worlds. Humanity's gaze at Mars has been filtered through technological progress, cultural imagination, and political currents. Cold scientific instruments and warming metaphors have both charted and inflated expectations. During the space age, political rivalry turned Mars into a stage for national accomplishment. Telescopic enthusiasts turned it into a place of romance and lament. Scientists turned it into a laboratory for paleo-environmental reconstruction. Technology translated distant light into data, rock compositions, atmospheric chemistry, isotopic ratios. Each dataset constrains the narrative and opens new avenues for interpretation. The more that was measured, the more complex the story became. Early romanticism gave way to layered realism, even as evidence for a watery past grew. So did awareness of how many processes could erase signs of life. Mars also occupies a unique psychological position because it is reachable. Unlike distant exoplanets, whose study remains largely indirect, Mars can be examined, sampled, and, within the limits of current engineering, visited. That proximity fosters an intimacy in human thought. Speculations about Martian civilization, therefore, are not merely literary. They feed into concrete decision-making, where to focus missions, which rocks to cache for eventual return, how to design instruments to test for complex organics. The practical and the philosophical converge. Every rover track across Martian regolith becomes a small, provisional footprint of human curiosity. There is, too, a long cultural litany of stories that frames Mars as other and as possible home. Novels, films, paintings, and songs have each reimagined the planet in ways that reflect contemporary anxieties. The fear of inhuman rivals, the hope of migration, the fantasy of salvage. During times of terrestrial crisis, visions of Mars often swell into proposals, escape routes for failing civilizations, or blank slates for utopian reinsertion. Conversely, the image of Mars as a desiccated wasteland serves as a parable for environmental collapse. In either frame, Mars functions as a narrative device that helps humans think through identity and responsibility. That narrative device has political weight. Decisions about exploration, about returning samples, about planetary protection protocols are not solely technical, they carry symbolic freight. Are missions intended to search for life or principally to prepare human settlement? The answer shapes instrument priorities, funding flows, and ethical frameworks. The speculative idea of a Martian civilization influences how institutions conceive of contamination risks, both forward contamination of Mars and backward contamination of Earth, and how they set thresholds for claims. The more the public imagines Mars as a world of former cities, the more scrutiny and debate will accompany each mission's purpose. Underneath these institutional debates are the quieter human reactions: wonder, melancholy, stubborn hope. There is a certain tenderness in the way people anthropomorphize a planet, attributing to it narratives of adolescence and senescence, of flourishing and decline. Poetry often captures this better than policy documents. The image of a planet that once hosted rivers and perhaps life invites lamentation for loss and curiosity about recovery. Even the term cradle carries ambivalence. A cradle implies care but also temporary support. It is the beginning of motion away from origin. To conceive of Mars as cradle is to suggest that something once small and warm matured and left, or was left, behind. Finally, to ask whether Mars ever hosted a civilization is to confront the limits of knowledge. Science can accumulate data, rule out models, and constrain possibilities, but it can rarely produce absolute closure for deep-time mysteries. There is no definitive archive for every question. What can be done, and what the human mind will continue to do, is to place hypotheses against the backdrop of planetary evolution, to weigh likelihoods, and to design experiments that increase the clarity of answers. The work is incremental and cumulative: an orbital survey that maps mineralogy, a rover that uncovers a stratified delta, a returned sample that yields complex organic signatures with isotopic patterns inconsistent with abiotic synthesis. Each piece of evidence is a small lamp in a cavern. If Mars was ever a cradle, its story, whether tragic or ordinary, would rearrange the contours of human self-understanding. If it was not, the question still serves as a profound mirror. It reveals the ways humans project their narratives into the cosmos and the urgency with which they seek continuity beyond their own fragile planetary span. The red planet in human eyes is both near and unknowable, familiar and alien, a site of scientific method and fabled longing. As the first chapter in a longer investigation, the simple, shocking question about a vanished civilization performs a dual function. It wakes curiosity, and it frames a moral inquiry. It demands both telescopes and philosophy, instruments and introspection. For now, the data settle into patterns. Mars was wetter once. It has minerals that bear water's fingerprints. It contains organic molecules in places where life could conceivably have persisted. At the same time, there is silence in many channels where the presence of past intelligence would demand a different signal. Structured, non-natural patterns that survive erosion and oxidization. Silence is not disproof, only a challenge. It insists on patience, on better tools, on humility. As humanity continues to listen and look, the red planet will keep performing its dual role as a subject of careful scientific inquiry and as a reflector of human meaning-making. The shock of the opening question does what any good question should. It unsettles complacency and focuses attention. Whether Mars was a cradle of civilization will remain, for now, an open inquiry. But the story of how humans have imagined Mars, responded to evidence, and integrated the planet into their ethical and philosophical thought is already rich, and it will only grow as new missions peel back the layers of a world that has been both neighbor and riddle for millennia. The next acts of that story will be written in soil, in spectra, in the quiet changes of policy, and in the louder changes of culture. But this opening, the question that casts Mars as either a lonely rock or an erased cradle, must be kept alive. It is the hinge on which a dozen more inquiries will turn, about the nature of life, the fragility of planetary climates, and the responsibilities of intelligence in a universe where time stretches longer than any single civilization. But now, Mars remains a promise and a warning, and human eyes and instruments will continue to pause its rust-colored face for whatever traces the indifferent passage of deep time has left behind. What does a dried riverbed say when read across deep time? The question lands like a pebble dropped into a still pool of curiosity, ripples of inference and longing spreading outward, gathering sediments of hope and caution. When humans look at the sinuous scars on Mars, they do not see mere grooves in rock. They see an argument written by water, wind, and gravity. Those grooves are sentences from a planetary biography, and the work of translating them is an exercise in both geology and imagination. From a distance, Mars's valley networks appear as delicate tracery etched into a rust-colored sheet. They branch like tributaries on Earth, tapering and combining, suggesting the slow, patient work of surface runoff. Closer inspection by increasingly capable spacecraft transformed hazy outlines into intricate topography. Orbital altimetry traced the relief of ancient drainage basins. High-resolution cameras resolved terraces, meanders, and perched deltas. Instruments that read mineral signatures found clays and sulfates in the channel's beds, minerals that form in the presence of water. Each instrument added a layer to the interpretive map. Valleys that once carried water, basins that once held lakes, deltas where sediment accumulated, and perhaps where organic molecules could have been sheltered from the ravages of exposure. The emotional contour of these discoveries is not purely scientific. There is a tenderness in the way the channels are spoken of, a whisper of melancholy threaded through the thrill of possibility. The valley networks are simultaneously proof that Mars had climates hospitable to liquid water and a reminder of the planet's shift into aridity. To stand, even vicariously, on a Martian escarpment and peer into a canyon is to inhabit two times at once, the far-off wet past and the present dust-strewn stillness. That doubleness colors the interpretation of every curve and deposit. The mind wants to complete the story. Did those channels host ecosystems along their banks? Did deltas trap organics and bury them beneath protective sediments? Could such places preserve a signature of biology, or of something more organized, more cultural? Geology offers a measured answer. Valley networks on Mars come in a variety of morphologies, each telling a different tale about water's role and duration. There are the branching, finer tributary systems that resemble terrestrial catchment networks. These suggest sustained precipitation and surface runoff, a climate very unlike Mars today. There are the broad outflow channels, gash-like corridors, hundreds of kilometers long, whose scale and erosive power imply transient, catastrophic floods. There are valleys that bear the signature of groundwater sapping, amphitheater-headed channels that appear to have been eaten back by springs issuing from subsurface aquifers. Then there are inverted channels, enigmatic ridges that were once stream beds and later became more erosion-resistant than their surroundings, standing proud as the less weathered remnants of flowing water. Taken together, these features sketch a world that experienced both slow, sustained hydrological cycles and dramatic bursts of fluid erosive energy. Timing is critical. Most of these valley systems date to the Noachian and early Hesperian epochs, roughly 4 to 3 NA. 500 million years ago, a window when Mars was bluntly more active. Crater counting techniques, combined with stratigraphic relations, place much valley formation in this ancient chapter. The Noachian Mars had higher rates of impact, volcanism, and, crucially, the right conditions for water stability on the surface. Clays formed in this era, minerals that on Earth are renowned for their ability to trap and preserve organic matter. The scenario invites a simple but powerful inference. If life, even microbial life, ever existed on Mars, this was the time and the place where its chemical traces would have stood the best chance of being buried and protected. But preservation is a contest. The same processes that record history also efface it. Mars is a planet of extremes, powerful winds that mobilize fine dust, radiation from a thin atmosphere that breaks molecular bonds, pervasive salts like perchlorates that can oxidize and destroy organics. Over geological epochs, the surface is a palimpsest, a manuscript repeatedly scraped and overwritten. Impact cratering FIP surfaces, exposing deeper materials and pulverizing potential archives. Volcanic resurfacing buries older landscapes beneath lava flows and ash. Aeolian deflation strips fine-grained sediments that might otherwise seal and protect organics. The relentless battering of cosmic rays percolates into the first meters of regolith, chemically altering organic compounds and complicating detection. Each valley, then, is both a repository and a battleground between memory and oblivion. Within that contest, certain depositional contexts become more promising as refuges for persistence. Deltas, for instance, concentrate and bury material rapidly. On Earth, deltas are the graves of leaves, cells, and molecules, places where rivers slow and shed their loads. A delta's internal stratigraphy often alternates fine and coarse layers, forming an archive of sequential deposition. Jezero Crater's delta, imaged in exquisite detail by orbiters, epitomizes this kind of potential. Its lobes, channels, and cross-bedded layers suggest a sustained period of sedimentation in a standing body of water. In sedimentary terms, This is the kind of place that, if life existed, might have collected and safeguarded molecular evidence. The emotional charge of such places is palpable. The delta is not just a target for instruments, it is a promise, a substrate where the planet might have locked away memory. Inverted channels complicate that promise in an intriguing way, where sediments carried by water become cemented, by minerals precipitating from groundwater, or by chemical processes that bind grains together. They can survive longer than the surrounding, less cemented deposits. Erosion then preferentially removes the softer matrix, leaving the once low-lying channel as a positive relief ridge. These inverted features are paradoxically easier to spot from orbit precisely because of their anomalous durability. They become beacons, pointing to routes where water once flowed and where material was concentrated and, perhaps, preserved. The presence of such inverted channels stirs investigative urgency. They are exposed cross-sections of ancient river systems, accessible without deep excavation, yet they arrived at their current state only after complex sequences of deposition and lithification. The mineralogical record deepens the story. Spectrometers have catalogued clays, sulfates, carbonates, and hydrated silica across valley floors and basin margins. Each mineral is a clue about the chemistry of past waters. Smectite clays, for example, form in neutral to alkaline conditions and can absorb and protect organic molecules. Sulfates, often associated with evaporation, can indicate more acidic, saline environments. Carbonates, if abundant, would imply the existence of atmospheres and waters that could support long-lived, temperate conditions. The patchwork of minerals suggests that Mars did not experience a single monolithic water regime, but a mosaic of niches with varying pH, salinity, temperature, and longevity. That heterogeneity is good news for the imaginative search for life. Fine-grained, neutral pH, rapid burial environments stand the greatest chance of preserving biosignatures. Yet the search for signatures of intelligence, material traces that unambiguously indicate contrived structure, faces a more stringent test. Geological processes can produce patterns that, at a glance, may look designed. Polygonal cracking from desiccation can mimic man-made tiling. Linear ridges from fracture-controlled erosion can resemble engineered walls. The observational standard for inferring intelligence is high. Geometry alone does not suffice. Ordered artifacts, repetitive tooling marks, alloys or anomalies in material composition that define natural processes would be required. And even then, timescales conspire against clarity. Over billions of years, mechanical weathering, micrometeorite sandblasting, and chemical alteration work to homogenize and rework surfaces. Thus, the plausible signatures of intelligence would most likely be large-scale modifications, massive quarries, monumental geometric alignments, or deep-buried artifacts, anything capable of surviving planetary vicissitudes. The absence of such compelling evidence in current orbital datasets pushes the inquiry back toward more modest but still profound questions about habitability and biosignature preservation. A second class of preservation arises from burial and shielding. Subsurface contexts, caves, lava tubes, and sediments many meters deep offer quieter chemical conditions. Radiation attenuates quickly with depth, and thermal gradients stabilize. If life ever found refuge under Mars's skin, its chemical legacy might still linger where cosmic rays do not pervade. Radar sounders have probed beneath the surface, revealing stratified layers, buried ice, and, in some locales, anomalous reflections that hint at interfaces between different materials. The idea that an archive could be hidden just out of sight lends an almost cinematic quality to orbital reconnaissance. The quiet hum of instruments becomes akin to a searchlight sweeping across an unreadable, layered history. The human act of selecting a site to explore is itself a narrative moment entangled with these scientific subtleties. Each chosen landing place is a proposal, a hypothesis about where memory might persist. The reasoning integrates geomorphology, mineralogy, and an assessment of preservation potential, deltas for burial, fine-grained lacustrine deposits for organic trapping, inverted channels for exposed stratigraphy, and regions with layered mineral assemblages for chemical context. Those decisions carry anticipatory affect, a field team's exhilaration when a rover finds cross-bedding in a Martian rock, that tightening of attention when organics appear in an unexpected suite. The composite of these moments is not melodrama but a sustained tension between expectation and the planet's stubborn silence. Attention must also be paid to the deceptive voices of earthly projection. The 19th century misreading of straight lines as canals stands as a cautionary parable about eager pattern-seeking. Humans are adept at detecting agency and order and symmetry, sometimes when none exists. Modern planetary science responds to that proclivity with rigorous frameworks, hypothesis testing, null models, and the principle that extraordinary claims require extraordinary evidence. Remote sensing specialists are careful to cross-validate morphological impressions with geochemical signatures and stratigraphic context. When a potential biosignature is flagged, the chain of custody, the contextual story of that signal, determines its credibility. Technological advances have steadily improved the resolution of that story. Orbital instruments now map mineralogy at tens of meter scales. Radar peels back tens to hundreds of meters of subsurface, and rovers characterize textures and chemistry at the scale of grains. Sample caching and eventual return could add laboratory-grade isotopic analysis to the roster of tools, allowing for discrimination between biotic and abiotic organic production by assessing isotopic fractionation patterns. Yet even laboratory work cannot always disentangle deep time ambiguities. Abiotic processes can mimic biological signatures, and preservation biases can skew the record. The strategy, therefore, is not to chase a single smoking gun, but to assemble convergent lines of evidence, morphology plus mineralogy plus isotopic inconsistency with known abiotic pathways. Amid all this technical deliberation, there lingers a philosophical strain. The valley networks are as much moral text as they are scientific. They ground thought experiments about fragility and contingency. A river that once flowed and then vanished is a lesson writ in stone about planetary thresholds. If Mars transitioned from a world capable of sustaining precipitation and lakes to a place of desiccation and radiative exposure, what does that say about planetary habitability as a dynamic condition rather than a permanent property? The valleys, in their silence, pose a stark question. How tenuous is the state that allows life to flourish for a species perched on an oceanic planet? The Martian record is an external mirror that dramatizes the stakes of climate, atmospheric loss, and the tenuousness of surface habitability. There is also, woven into the valley narratives, an ethical dimension to exploration. The selection of landing sites, particularly those that might archive biosignatures, raises concerns about forward contamination. The act of bringing Earth microbes to fragile Martian sediments could obscure the very signals seekers hope to detect. Planetary protection policies, therefore, are an integral part of how humanity reads Mars's dry valleys. They are both a scientific precaution and a moral commitment to preserving an independent record. That responsibility is an unglamorous but profound part of the work, to look without spoiling, to interrogate without imposing. As instruments continue to map and missions to sample, the dry, caked valleys will remain among the most eloquent terrains on Mars. They are places where the planet's climate history is articulated in curves and strata, where preservation advantages and erosive perils are interleaved, and where the hope of discovering traces of past life or complex activity is most concentrated. They compel a particular kind of patience, a patience that appreciates stratigraphy, respects context, and resists the seductive rush to sensational conclusions. In the end, reading Mars's valleys is a humane act as much as a scientific one. It requires humility before deep time, meticulous assembly of evidence, and a tempering of imagination with method. The dried riverbeds are not merely geological features, they are pages from a planetary ledger, inscribed by water and smudged by wind. For those who watch and interpret, they offer both a window into what Mars was and a mirror reflecting human curiosity, an enduring desire to find kinship in the cosmos, to learn from vanished climates, and to guard the fragile possibilities of habitability where they are found. The valleys may keep their secrets for centuries more, or they may, with patient exploration, yield a small, luminous shard of memory. Either outcome will deepen the conversation about life, loss, and the scales of time on which both are measured. Imagine for a moment a planet whose breath thins and then stops, not as a sudden suffocation, but as a slow ebb, like a bonfire reduced to embers by an indifferent wind. That image hangs at the center of the question. Mars, which once held standing bodies of liquid water and an atmosphere capable of carrying weather, became a world whose air is now barely a whisper. How does a planet lose its breath? And what does that loss tell the watcher who reads landscapes as if they were sentences from a vanished language? The first part of the story has been told in scars, valleys, deltas, sinuous channels that once threaded the surface. The earlier chapters asked whether some of those scars, the curious linear features, the symmetrical terraces, the regular ridges, might hint at artificial shaping. Skepticism, the best companion to wonder, reminded observers how nature can dress itself in patterns that resemble design. Yet the deeper, less speculative question now is not only whether water carved those forms, but how The very atmosphere that allowed water to exist itself disappeared. That disappearance is a keystone in any attempt to read the planet's past, because atmosphere and water are two partners in planetary habitability. One cannot be understood without the other. Evidence accumulates in many forms. Some of it is geological, minerals that only form in the presence of water, layered sediments that could have been deposited in lakes, deltas that suggest persistent flows. Some of it is chemical and isotopic. The ratios of heavy to light hydrogen, the signatures of carbon, the oxidized nature of surface materials. And some of it is direct, dynamic measurement of the processes that continue to drain the planet even today. Together, these lines converge on a narrative. Mars once wore a thicker cloak of gases and, with that cloak, a climate capable of supporting liquid water on the surface. Over deep time, that cloak thinned until the climate flipped into a cold, hyper-arid state. What could unmake an atmosphere? There is no single villain but a cast of processes, each interacting with planetary properties and the larger environment of the solar system. One of the central elements is the loss of a protective global magnetic field. Remnant magnetization locked into Martian crust suggests that, very early on, Mars possessed an internal dynamo, a molten, convecting core capable of generating a magnetic field that would have knitted the planet's upper layers into a shield against charged particles from the sun. Geological evidence indicates that this dynamo waned and then ceased. Without such a shield, the solar wind, a stream of charged particles and magnetic fields flowing outward from the sun, was able to sweep away the upper atmosphere more effectively. The mechanics of atmospheric escape are many. Solar ultraviolet light breaks apart water molecules in the upper atmosphere. Their hydrogen atom fragments, light as ghosts, can achieve velocity sufficient to escape the planet's feeble gravity, especially when heated during periods of strong solar activity. This photodissociation leaves behind heavier oxygen, which can react with surface materials or be lost via sputtering, a process in which incoming energetic particles physically knock atmospheric atoms into space. Coronal mass ejections and intense solar storms increase such stripping episodically. Over millions to billions of years, the cumulative effect is enormous. The light fraction of water disproportionately departs, leaving the residual volatiles depleted and isotopically heavy. Isotopic evidence is among the most persuasive records of that history. Measurements of the ratio of deuterium, heavy hydrogen, to ordinary hydrogen in Martian water show enrichment compared to Earth's oceanic standard. Because lighter hydrogen escapes to space preferentially, the remaining reservoirs are enriched in the heavier isotope. The elevated deuterium to hydrogen ratio in Martian samples and in the planet's atmosphere today speaks of a past with far more. Water that has been preferentially lost to space. This isotopic fingerprint is a ledger item. Water once existed in abundance, and much of it has gone. Spacecraft have not only taken static fingerprints, but have watched the process unfold. The MAVEN Mars Atmosphere and Volatile Evolution mission, carrying instruments designed to sample the very flows of particles at the interface between planet and space, measured ongoing atmospheric escape. Its sensors observe the ways ionized particles are carried off by solar wind interaction, documented how energetic events spike escape rates, and tied atmospheric loss directly to the lack of a global magnetic shield. These measurements quantify a continuing leak, a slow but persistent drain. Yet the loss story is not one of simple, continuous evaporation. Mars's atmospheric retreat likely involved feedbacks, punctuations, and detours. Volcanic outgassing in the planet's youth may have replenished the air episodically, while impact events could strip atmospheres suddenly or trigger transient greenhouse episodes. Chemical sequestration also plays a role. CO2 may have been converted into carbonate minerals, locked into rocks, or drawn down into the crust through aqueous alteration. The discovery of carbonate-bearing deposits is tantalizing but limited. The global reservoir of carbon locked in rock does not fully account for the vast atmosphere that will be needed to sustain long-term warm climates. Thus, the narrative must incorporate both physical escape to space and internal sequestration. Both can be significant. Both tell different tales about what environments were once possible. The consequences of atmospheric thinning extend beyond the disappearance of surface water. As pressure declines, the boiling point of water drops and the capacity for liquid stability diminishes. Temperatures fall as greenhouse gases are removed. The loss of an ozone layer, absent robust atmospheric chemistry and a shield against ultraviolet light, leaves the surface exposed to sterilizing radiation. chemical reactions on the surface, driven by the interaction of oxidants like perchlorates with organics, further erode the chemical traces of any past biology. The net effect is that by the time Mars cooled and dried, the surface environment became doubly hostile, cold and bathed in ionizing radiation and oxidants that break down complex organics. That hostile present is essential context when the watcher asks whether any artifacts of intelligence could have endured. Time is an unforgiving conservator. Human structures on Earth can persist for centuries and millennia under favorable conditions, but the Martian environment is relentless in different ways. Micrometeorite bombardment, thermal cycling, chemical oxidation, and wind abrasion sift and sand any exposed material. Over hundreds of millions to billions of years, even robust stone can be pulverized, metals corrode, plastics, if they are a plausible speculatory material, undergo radiation-driven breakdown. The only routes to long-term preservation are either enormous scale, structures so massive that planetary resurfacing cannot erase them, or burial and shielding which hides relics beneath layers of rock and sediment, fossilizing them against the cosmological weather. This is where the imagery of canals and linear features returns, now reframed by the atmosphere's departure. What looks like an engineered waterway from afar might be an inverted channel preserved by cementation. What appears as a straight wall may be a tectonic fracture or a dike, a cooled filament of igneous rock that naturally forms linearity. Yardangs, streamlined ridges carved by wind, can create regularity that feels deliberate. Polygonal cracking of permafrost can yield grid-like arrangements. The human brain, evolved to detect agency, is quick to read pattern as purpose. Science counters with method, repeat observations, cross-disciplinary corroboration, and predictions about what would be expected from natural processes versus those from cultural activity. If intelligence did leave marks, the likely repositories for durable signals are beneath the surface. Lava tubes in caves are natural vaults. Their ceilings protect against radiation and wind, and their interiors can preserve delicate organic chemistry far longer than an exposed plain. Subsurface ice and permafrost can act as cold anchoring matrices that slow chemical decay, radar sounders that probe subsurface layering, and seismometers that record interior structure become instruments of archaeology as much as of geology. The idea that a civilization's faint footprints could be waiting encoded in subsurface strata is at once thrilling and humbling. Thrilling because discovery would be epical, humbling because the scales of time and burial required are beyond everyday intuition. There is a profound moral and pragmatic dimension to this history of atmospheric loss. Observing a planet that transitioned from relatively clement conditions to a desiccated, sterilized surface poses a mirror to any species privileged to witness it. That mirror is not only scientific but ethical. It asks what responsibilities come with the knowledge of planetary fragility. For the planetary scientist, the imperative is both to learn and to preserve, to design missions that can read Mars's buried stories without overwriting them with terrestrial microbes. Forward contamination is not merely an operational constraint, it is a commitment to maintaining the integrity of another world's record. The atmospheric tail also reshapes the stakes of exploration. Instruments must be chosen to pierce layers of obfuscation, spectrometers to trace isotopic histories, drilling systems to reach shielded horizons, radar to detect buried voids, and sample caches to ferry material to Earth laboratories capable of nuanced chemical discrimination. Each technological choice is an ethical act, which deposits to excavate, which valleys to traverse, which sediments to sample. The selection of a single landing site is a gamble in historiography, a bet that the chosen patch of Martian ground will be the one that preserves and reveals the clearest pages of the planet's biography. Beyond instruments and ethics, the atmosphere's disappearance reframes myth and imagination. Mars, in human eyes, oscillates between warning and invitation. Its pale deserts are cautionary tales about the fragility of habitable climates. Its ancient basins are invitations to understand the conditions that permit life to arise and to persist. The atomization of gases into space is, in narrative terms, a slow erasure of possibility. It teaches humility. To study Mars's lost air is to accustom oneself to questions that are not immediately solvable and to appreciate the patient accumulation of evidence that slowly reshapes hypotheses. There remain inevitably alternative accounts and uncertainties. The precise pressure of a Noachian Mars, the duration of warm windows, the degree to which volcanism replenished volatiles, and the balance between sequestration and escape are all subjects of ongoing study. Models differ, and new data can tilt interpretations. Yet the broad outlines have hardened. Mars was once different in ways crucial to biology and planetary climate. The loss of its atmosphere explains, at least in part, the shift from that earlier state to the present one. Finally, the narrative invites a last reflection that cuts across the technicalities. The scale of planetary change reminds observers of the transience of any single epoch, human or otherwise. Time in planetary terms is patient and indifferent. Civilizations, climates, and even magnetic dynamos are episodes and trajectories measured in hundreds of millions to billions of years. Reading Mars's atmosphere as a vanished partner to water brings with it a salutary modesty. The question is no longer a quaint curiosity about canals or hypothetical monuments. It becomes a meditation on thresholds and resilience. Understanding how Mars lost its breath is to confront how fragile the conditions for life can be, how rare and precious stable habitability might be, and how careful a species must be when it contemplates altering the breath of a world. The breath that left Mars does not speak. Its sigh is recorded in chemistry and topography, in thin air and salty soils. The story requires patience to decipher and a humility to interpret. It is, in the end, a story that connects the geological and the moral, a record of processes that unfolded across deep time, and a warning to any mind that would take planetary scales for granted. To watch Mars in this frame is to watch a mirror of sorts, and to make choices based on the awareness that atmospheres are not immutable. They can be built, sustained, and, tragically, they can be lost. The implications ripple outward for the search for life, for the reading of potential artifacts, and for humanity's own stewardship of the thin envelope of air it calls home. What would it mean to find, amid the rust and the dust, the ghost of a city? The image lodges like a shard of light through a crack. An entire urban organism reduced to a shadow, a faint registry of geometry and mass that once hummed with systems. The question is not simply archaeological, it is epistemological. How does one read absence when the absence itself might be a distorted, weathered presence? How does an observer distinguish a natural pattern worn into the landscape from the deliberate imprint of minds? The possibility opens a corridor of inquiry that blends geology, material science, planetary physics, and a peculiar human longing to find continuity beyond frailty. At the scale of the orbital viewer, the idea of ruins must begin with scale and endurance. Cities that endure on Earth do so because of favorable conditions, durable building materials, relatively protective climates, and sometimes the accident of burial. On a planet exposed to micrometeorite rain, ionizing radiation, wind-blown sand, and chemical oxidants, durability is tested relentlessly. A city's visible superstructure, streets, facades, towers, would be the first to succumb. Wind abrasion would sand sharp edges into rounded forms, thermal cycling would fracture and pulverize brittle components, chemical processes would oxidize and leach elements, impacts could fragment and scatter. Over epochs, exposed architecture would devolve into sedimentary signals, anomalous lumps, unusual textures, pockets of dense material buried beneath aeolian veneers. If a vanished civilization had once existed on a planet that later desiccated, the most plausible place for traces to survive is not on the surface, but in the earth beneath it. Burial is the planet's best archivist. Rapid sedimentation in lake beds or deltas can entomb delicate materials, isolating them from radiation and abrasive winds. Lava tubes and cave systems offer vaults where artifacts could be shielded for geologic epochs. Deep burial within permafrost or within sedimentary layers that lithified into rock arrests many of the chemical pathways that would otherwise obliterate organics and fine microstructures. Thus, the search strategy for ancient urban traces necessarily focuses on substrata, places where mass anomalies, geophysical discontinuities, or stratigraphic surprises might indicate buried structures. What, then, would such buried evidence look like to instruments that do not carry human eyes? Gravity and magnetic surveys would be the first hints of something anomalous. Large-scale constructions of dense materials, slag heaps, foundations, buried metal masses would register as local gravity highs or magnetic anomalies. Orbital gravimetry can detect mass concentrations that deviate from expected geology. Magnetometers can reveal patterns in remnant magnetization that do not conform to sedimentary models. But the signal of an artifact must be discriminated from natural causes, intrusive igneous bodies, fossilized load-bearing sediments, or mineralized veins can produce comparable responses. The challenge is one of pattern and context, of integrating multiple sensor modalities to favor one explanation over another. ground-penetrating radar and subsurface sounding complicate and enrich the picture. Radar echoes can reveal voids, layered bedding, and abrupt contrasts in dielectric properties that might correspond to walls, vaults, or fills. Inverted channels, compacted layers, and cemented sediments carry electrical signatures that differ from loose regolith. A radar profile revealing rectilinear voids or regular spacing of reflectors would be striking. Yet even regularity is not proof. Nature can fashion orthogonality through cooling fractures in lava flows, polygonal desiccation patterns in clay-rich sediments, or jointing in sedimentary rock. The documentary question becomes, what degree of regularity across what set of observables would tip the balance from plausible natural formation to credible intentionality? Materials chemistry offers perhaps the most discriminating tests. High-temperature processes, metallurgy, glass-making, ceramic firing leave signatures that deviate from common geochemical pathways. Ceramic glazes, vitrified slag, industrial glass, and alloy microstructures are chemically and structurally distinctive. If a buried layer contained concentrations of non-native alloys, unusual phase assemblages, or glassy slag with textures characteristic of smelting, that would constitute a strong line of evidence for anthropogenic processing. Equally telling would be isotopic anomalies. Large-scale industrial activity acting on planetary reservoirs can fractionate isotopes in ways that differ from natural fractionation. While natural processes can produce odd isotopic ratios, complex and repeated fractionation patterns associated with manufacturing could reveal an imprint of intensive, localized chemical processing. But time is an unkind conservator. Metals corrode, glass devitrifies, and polymers break down under radiation. What might appear as a definitive metal alloy a million years ago could now exist only as a segregated assemblage of oxides and altered phases, its original alloying elements redistributed into soils. Carbon-based polymers, if they ever existed, may have been converted to graphite-like residues or scattered as microscopic carbonaceous spherules indistinguishable from abiotic organic matter produced by hydrothermal processes or meteoritic influx. Even so, some high-temperature artifacts are remarkably resilient. Fused glass and certain ceramics can survive extreme chemical and thermal cycles, preserving microstructural clues that betray complex manufacture. On Earth, shards of ancient pottery and slag survive for millennia on a dry, low-oxygen planet with minimal biological activity. Those same materials can persist for far longer if they remain buried and shielded. Large-scale landscape modifications would be easier to detect than fragile household artifacts. Quarries, open-pit excavations, artificial terraces, linear transport corridors, or stepped embankments leave macro-scale scars. A civilization that extracted ores or diverted water would rework volumes of material that might alter drainage or sediment thickness appreciably. Such modifications would be visible to orbital topography and radar as anomalies in layer continuity or as terraced geomorphology inconsistent with natural slopes and depositional patterns. Again, the key is integration. Does a topographic anomaly align with mineralogical concentrations consistent with extraction? Does the stratigraphy show abrupt truncation and replacement by engineered fills? When features co-occur across independent datasets, the hypothesis of deliberate alteration gains traction. The specter of false positives looms large. Humans have a psychological proclivity for seeing agency in regularity. The 19th century misreading of planetary streaks as canals offers a cautionary tale. Observers eager for orderly design can mistake natural processes for craft. On other planets, processes like columnar jointing, dike swarms, fracture-controlled erosion, and mineral vein deposition can display striking linearity and apparent regularity. Sedimentary bedding, later tilted and exhumed, can present stacked terraces that mimic urban platforms. The scientific safeguard against such misclassification is methodological pluralism, independent measurement techniques, repeatability, and an insistence on convergent evidence before assigning cultural causation. Another dimension of inquiry concerns energy and its anisotropic traces. Any civilization capable of large-scale construction would have to manage energy to extract, transport, and transform it. Energy-intensive processes generate thermal, chemical, and isotopic footprints. Large kilns or furnaces might create localized, thermally altered zones where rock is melted, annealed, or recrystallized at temperatures inconsistent with regional metamorphism. Widespread use of fossil-like fuels or concentrated combustion could leave layers enriched in soot, polyaromatic hydrocarbons, or chemically altered mineral surfaces. Certain industrial catalysts incorporate rare elements. A concentrated enrichment in unusually distributed trace elements could signal purposeful concentration and use beyond geochemical randomization. Again, natural analogs exist. Hydrothermal systems can produce unusual chemistries, but the spatial and stratigraphic patterns of industrial use would differ from diffuse natural processes. Orbit is an ephemeral archive in long time frames. Satellites, debris, and orbital structures are subject to perturbation by solar radiation pressure, gravitational resonances, and collisional diffusion. In the space of millions to billions of years, orbital systems are likely to degrade or re-enter. The most persistent spaceborne signatures would be mass concentrations or orbital debris that, by some pathway, became surface material through decay or impact. Thus, while the detection of ancient orbital megastructures is a tantalizing image, the physics of orbital decay favors deep subsurface and surface relics as more reliable targets over geologic time. Even the notion of an erased city must reckon with scale. A metropolis the size of Damascus or Rome, composed mainly of organic matter and modest stonework, would vanish more completely than a city built of engineered, vitrified materials or massive monoliths. The larger and more integrated the construction, the greater its chance of leaving a detectable imprint. Monumental earthworks, deep foundations, mass-produced ceramics, or large-scale hydraulics would be much more resilient than delicate ornamentation. If a past civilization practiced mining on a planetary scale, the geophysical footprint would be correspondingly pronounced. Depletion halos, slag gradients, and disrupted stratigraphy visible to large-scale surveys. There is another possibility, the redistribution of biospheric reservoirs. A technicized civilization might have altered soils, deposited synthetically produced carbon, or created reservoirs of processed materials, plastics, composites, in quantities sufficient to change the planet's sedimentary record. Over eons, polymers degrade, but their carbon can be sequestered in horizons that differ from background organic content. For instance, through unusual isotopic ratios or distinct molecular fragments. Detecting such signatures would require return samples and laboratory analysis capable of isolating molecular peculiarities from abiotic organic inputs delivered by meteoritic dust or endogenous synthesis. Planetary protection and the ethics of detection complicate the hunt. The act of investigating potential sites risks contaminating them with terrestrial microbes, obscuring the very signatures sought. The documentary impulse to know must be balanced against the obligation to preserve. Instrumentation must be calibrated for sensitivity without compromise. Mission planners must prioritize sterile sampling and consider in situ analysis that reduces the need for invasive excavation. The imperative is not just scientific, but custodial, to read another planet's ledger without writing in it. The emotional current running beneath these technical deliberations is unmistakable. The possibility of ruins that hint at former cityscapes provokes awe, a humbled quiet before time's immensity. It evokes melancholy for the vanished, whether biological or cultural, and a sober reflection on the fragility of any complex system. A discovery of such magnitude would reframe human understanding of longevity, resilience, and the contingency of civilization against planetary processes. It could read as a warning or a mirror, a demonstration that complex arrangements can be transient, that habitability can be lost, and that the artifacts of intelligence are not guaranteed immortality. Yet the search is not merely existential. It is methodical work, mapping, cross-validation, cautious interpretation. The most plausible path to any confident conclusion is incremental. Orbital surveys flag anomalies, subsurface probes refine the shape of the anomaly, in situ instruments assess mineralogy and microstructure, and ultimately, samples returned to laboratories permit the detailed isotopic and metallurgical detective work. That can exclude natural origins. At each stage, the standards of evidence must remain elevated. Because the cost of false inference is not merely reputational, it reshapes the narrative of life in the universe. There is also a poetic dimension to the silence of ruins. Silence is not absence. It is a form of testimony that needs translation. The faint, regular scars that persist on a plane may read as a civic plan only when integrated across time and medium, topography, chemistry, magnetics, and isotopes. The picture assembled from these disparate threads could be subtle and ambiguous, and yet it would teach profoundly. Even the continued absence of artifact-level evidence is information. It sets constraints on the kinds of activities that could have occurred, the scales at which intelligence must operate to leave durable traces, and the probability that a planet like Mars ever hosted complexity beyond the microbial. In the end, the The prospect of silent ruins is an invitation to patience, humility, and interdisciplinary rigor. It invites a perspective that treats absence and presence as complementary data, each bearing its own set of stories. Whether searchers ultimately find a buried metropolis or only a stack of geological anomalies, the endeavor will expand the ways in which minds on Earth understand time, preservation, and the signatures of complexity. The ruins, if they exist, will not shout. They will whisper through mass anomalies, through peculiar mineral assemblages, through stratigraphic discontinuity that refuse to be purely geological. To hear those whispers requires instruments, method, and a willingness to let silence teach as much as discovery. What if the sharp-angled glimpse in a dusty satellite frame is not merely a trick of light and shadow, but the remnant of intention? The question lands not as an answer, but as a hinge, a narrow image that swings open a room full of hypotheses. From orbit, certain patches of Martian regolith read like the faint glyphs of a language almost erased, low-relief mounds that suggest pyramidal geometry, aligned ridges that hint at grids, and mesas whose profiles from one orbital pass look like capstones or statue heads turned to the sky. Are these shapes the quiet footprints of design, or are they the product of geological choreography and human pattern-finding? The deliberation that follows is not a melodramatic hunt for treasure. It is instead the careful work of a discipline, learning how to listen to a planet that speaks in ambiguities. The initial images arrive as provocations, narrow-angle photos that pick out edges, high-contrast swaths where sunlight grazes across dunes, and radar returns that betray subsurface irregularities. Each dataset is a dialect. None speaks plainly. The heart of the investigation is therefore methodological, to translate pixel and radar echo into probability, to weigh prior plausibilities against observation, and to resist the seductive certainty of a single striking frame. Pareidolia, the brain's talent for finding faces in clouds and creatures in constellations, is the first guardrail to be acknowledged. Humans are exceptionally good at converting irregularity into story. That capacity has driven art and myth for millennia, and it can also mislead scientific inquiry. The lineaments that look like walls or pyramids from a particular angle often dissolve into natural processes when viewed across. Illumination, wavelength, and season. An apparent head can be a mesa whose flanks are rimmed with wind-polished strata. A seeming avenue can be a string of eroded dikes or a row of yardangs aligned by prevailing winds. The skeptical mind notes how many forms emerge depending on the instrument, the visible light camera, the infrared mapper, the radar sounder, the altimeter. If a shape persists across modalities and temporal conditions, its anomaly becomes harder to dismiss. To move from suspicion to credible inference requires a choreography of instruments. High-resolution imagery supplies geometry, stereo imagery, and laser altimetry render three-dimensional relief. Multispectral and hyperspectral instruments reveal mineral chemistry. Radar peels the shallow subsurface. Gravimetry and magnetometry measure mass. And magnetic contrasts. Together, these modalities can tell a more comprehensive story. Whether an apparent geometric structure is texturally consistent with igneous intrusion, wind-carved bedrock, or a concentration of dense, non-native material. When multiple independent lines converge on an interpretation, the posterior probability shifts. The task of the scientific community is to construct this convergence while continuously testing alternative natural explanations. Consider, for example, a small cluster of low, triangular mounds that from one orbit look uncannily like stepped platforms. A simple analysis might stop at the visual resemblance, but the rigorous sequence is different. First, stereotopography determines whether the edges are rectilinear or merely facets of a more rounded form. Next, spectral signatures assess whether the surfaces host minerals indicative of clay-rich sediments, volcanic glass, or vitrified slag. Radar sounding probes for coherent subsurface layering. An engineered foundation would appear as abrupt, laterally continuous reflectors, inconsistent with depositional bedding. Gravimetric anomalies might reveal higher than expected mass concentration beneath the feature, suggesting material density atypical for the surrounding lithologies. Only when these disparate datasets align does the anomaly graduate from curiosity to candidate for deeper investigation. Even then, the probability calculus remains conservative. There are abundant natural processes capable of producing surprising regularity. Cooling processes in igneous rocks create columnar jointing and orthogonal fractures that, when exhumed, display repeated, seemingly geometric forms. Sedimentary bedding, cut and tilted by faulting, can present terraces and rectilinear facets that mimic platforms. Wind and dust can polish and abrade cliffs into linear ridges. Mineral precipitation from groundwater can cement channels into resistant bands that stand in relief as quasi-architectural lines. The burden of proof for assigning an artificial origin is therefore high. Multiple independent anomalies, pattern consistency across scales, and mineral or isotopic signatures incompatible with known geologic pathways. There is also a temporal challenge. Even if an artifact was once monumental, deep time works relentlessly. Micrometeorite bombardment, thermal fracturing by dramatic diurnal temperature swings, oxidative chemistry driven by perchlorates, and the steady polish of wind-blown silica grains each conspire to degrade surfaces. Over millions or billions of years, sharp corners, round edges slump, and complex alloys corrode into diffuse oxide halos. The traces most likely to survive are those either extremely massive in scale or deeply buried. That is why subsurface investigation is not a luxury but a necessity. Buried architecture would be preserved in a way surface ornamentation is not, sealed beneath lacustrine deposits, entombed in deltas, or sheltered in lava tubes. The instrumental promise is therefore twofold: to seek anomalous geometry and to seek anomalies in chemistry. High-temperature processing leaves specific fingerprints. Vitrified slag, glassy residues with quenched textures, and alloy microstructures altered by purposeful metallurgy are distinct from products formed by lava flow or impact melting. Isotopic fractionations produced by controlled chemical processes, enrichment or depletion patterns in particular elements, could constitute a line of evidence for non-natural processing, yet caution persists. Hydrothermal systems and impact-related melting can mimic many of these signatures. The crucial differentiator would be pattern, spatially localized concentrations of chemically transformed materials in contexts inconsistent with known natural systems, especially when paired with geometric and stratigraphic anomalies. Remote sensing can place limits as readily as it can make suggestions. Radar sounders like Charad and Marsus chart subsurface reflectivity and can reveal interfaces that correspond to voids or layers of differing dielectric properties. A radar reflector network that aligns in rectilinear arrays would be striking. Gravimetry can map density contrasts. A buried foundation of dense, processed material would register differently than surrounding sedimentary rock. Magnetometers can pick up remnant magnetization patterns that diverge from regional magnetic fabric, particularly where high-temperature processing created localized thermal demagnetization or induced remagnetization in uncommon orientations. Each of these tools reads the planet with a different sensitivity, and together they can triangulate unusual contexts. Yet satellites alone often cannot close the case. The moment of greatest apprehension, the point where speculation yields to definitive interpretation, frequently requires in situ sampling and laboratory-grade analysis. A return sample can be examined for microstructural evidence of manufacturing, slag textures, non-equilibrium phase assemblages, alloy compositions, and isotopic systems resolvable at parts per million. The laboratory reveals microscopic clues, crystalline habits that require directed cooling, particulate morphologies that imply industrial combustion, trace element patterns indicative of ore processing. Those are the sorts of signatures that could move an argument from speculative intrigue to scientific plausibility. Even with samples, absolute certainty is elusive. Abiotic pathways continue to surprise. Shock, metamorphism, and impact events can produce glasses in high-temperature phases. Hydrothermal alteration can concentrate metals and produce unusual isotopic signatures. The interpretive path therefore rests on convergent lines, not single artifacts. A buried mass concentration, co-located with vitrified layers, spatially patterned via rectilinear plan geometry, and associated with isotopic fractionations inconsistent with known abiotic pathways, would be a compelling constellation. Anything less demands humility and restraint in claims. Beyond instruments and geology lies the human dimension, the response of watchers on Earth when an image glows with suggestion. There is a particular cadence to that reaction, a quick spike of excitement, then a sobering descent into methodical testing. The emotional arc is understandable and instructive. It reveals how hope and caution interleave in the practice of planetary science. The temptation to declare discovery is tempered by institutional norms, peer review, and a recognition that false positives in deep time are easy to conjure and difficult to unmake. That ethic of skepticism is not obstinacy. It is the custodian of credibility in the most consequential of inquiries. There are also practical constraints to consider. Even if an anomaly reaches the level of credible candidate, mission architecture imposes choices. Where to land, how deep to drill, how to design a sampler that preserves context and prevents forward contamination. Planetary protection protocols add another layer of deliberation, obliging exploration teams to weigh the value of invasive investigation against the risk of altering the very record they seek to read. The ethical dimension is as real as the technological one: to probe without polluting, to excavate without erasing. The conversation about pyramids and statues on Mars is thus more than a debate about ornament. It folds into larger questions already laid out by the geological record: the epochs when water persisted long enough to deposit sediments, the windows when a thicker atmosphere permitted warmer climates, the processes that could entomb material rapidly and thereby enhance preservation. The hypothesis that Mars once hosted organized activity hinges on plausible habitats and plausible modes of preservation. Deltas like that in Jezero crater become more than targets for organic search. They are also archives where the kinetic energy of flowing water could have buried and shielded cultural material. Lava tubes and subsurface caverns, meanwhile, are potential vaults that could harbor microenvironments less exposed to the planet's erosive toolbox. Ultimately, the question of geometric anomalies is also a mirror. It reflects human willingness to reckon with absence and to construct protocols for reading that absence. Whether the enigmatic angles are natural or cultural, the process of investigation sharpens methods, demands interdisciplinary rigor, and fosters an ethic of restraint. It teaches how to translate wonder into testable hypotheses, and how to balance the hunger for revelation against the slow patience of certainty. If the patterns are natural, they still carry meaning. They will have taught scientists about processes that create surprising regularity, about erosion and cementation operating at planetary scales, and about the limits of perception under restricted perspectives. If they are cultural, even fragmentarily preserved, the implications are profound: a rearrangement of assumptions about the ubiquity of intelligence and about the fragility of civilizations in geologic settings. But the in-between day of discovery, the long stretch of methodical testing, instrument cross-validation, and incremental sampling, is itself instructive. It cultivates humility in the face of time, and it trains a species to read other worlds not as storybooks, but as layered archives whose testimony must be assembled patiently. In the end, those shard-like images that first triggered wonder are less like final answers and more like invitations. They invite a sequence of readings, each deeper and more discriminating than the last: optical geometry, spectral chemistry, radar stratigraphy, gravimetric mass balance, in situ microanalysis. They invite an ethical stance that prioritizes preservation and rigorous proof. They invite an acceptance of uncertainty, and above all, a readiness to learn from silence as well as from discovery. Whether the angles are accident or artifact, the labor of interpretation will continue, slow, exacting, and rich with implication for what it means to look for companionship in the cosmos and to recognize, in the margins of rust and dust, the faintest traces of a vanished mind. What does the final act of a civilization look like when read at the scale of geology? Not as a headline or a hero's fall, but as a sedimentary layer, a chemical spike, a rearrangement of planetary skin. The question is vast because the timescales are vast: minutes of panic, years of collapse, and then eons in which wind, radiation, and chemistry conspire to smooth, scramble, and sometimes strangely preserve the last traces of what once was. When a planet that had been vibrant, rivers running, atmospheres thick, biospheres humming, becomes a tune, the narrators are not individuals but processes. Those processes write in ash and metal and isotopes, and the job of later readers is to translate a palimpsest into a story of catastrophe, natural calamity, technological war, or the murky interplay between both. Consider the moment of catastrophe as an author might sketch it: a sudden global blanching of skies, or the slow tectonic unwinding that turns fertile plains into ash-choked deserts. These are cinematic images, but more useful for thought than for direct detection across deep time. The signatures that survive are less dramatic in the instantaneous and more eloquent across stratigraphy. A spike of iridium in a clay horizon speaks of an impact. Shocked quartz and microtectites record an explosive encounter with cosmic rock. Thick layers of glass and charcoal tell of conflagration on scales that outclass volcanic events. Vast volumes of volcanic ash, their chemistry and thickness mapped over continents, narrate episodes of mantle unrest that can dim climates and rearrange ecologies. Those are the sort of natural catastrophes that can take a thriving planet and silence it over generational time. Technological annihilation writes different kinds of signatures, and those signatures are sometimes more human, the fingerprint of industrial intent, however catastrophic. Nuclear exchanges would leave a geochemical ledger, radionuclides with half-lives long enough to be detected in sediments millions of years hence, anomalies in xenon isotope ratios from fission products in excess of plutonium isotopes embedded in deep lake clays or peat bogs. The thermal intensity of nuclear blasts can vitrify soils locally, producing melt glass with textures and trace element patterns inconsistent with volcanic glass. An industrial thermonuclear war on a planetary scale could alter global albedo through soot injection, trigger abrupt cooling, the so-called nuclear winter, and set in motion biospheric collapse that would be visible as a sudden reduction of organic carbon flux in sedimentary records. Other technological paths leave more subtle, then increasingly exotic traces. The systematic deployment of synthetic materials at planetary scale creates layers in the geological record that otherwise would not exist. Plastics, for example, are a key case. At first glance, polymers weather and chemically transform in ways that make their direct detection over millions of years unlikely. Yet they fragment into persistent microplastics and can incorporate into sedimentary matrices. Their carbon may eventually become a diffuse, chemically altered horizon. But certain synthetic additives, halogenated flame retardants, uncommon organometallic stabilizers, might resist complete breakdown and be detected in trace concentrations. Such molecules would read as massive anomalies, complex, chirally symmetric, industrially specific organics in a context where abiotic synthesis or straightforward biotic production is implausible. Other signatures are even less ambiguous. Large-scale metallurgical activity concentrated in defined regions will leave heavy metal enrichments that do not match background geochemistry. Smelting produces slag fields, glassy, vitreous byproducts with specific microstructures. The scale matters. A few scattered slag shards could be geologic noise, but kilometer-scale slag deposits, stratigraphically bounded, demand societal explanation. Isotopic fractionation from industrial processes where elements show enrichment or depletion in ratios inconsistent with natural fractionation offers another window. For example, steelmaking and ore refining can concentrate particular isotopes in waste streams if these waste streams are later buried. The isotopic signatures can be preserved. The idea of a technological war triggered by self-amplifying technologies adds another speculative but plausible layer to the record. Nanoscale replicators or molecular assemblers, were they to escape control, might leave a diffuse chemical signature rather than monuments. One could imagine a sudden increase in certain surface textures, pitted, etched patterns on mineral grains produced by aggressive chemical processing, or the presence of synthetic nanomaterials embedded in sediments. Some nanomaterials are designed for durability, graphene-like residues or refractory carbon allotropes might resist chemical reworking and remain detectable as anomalous particulates. But the same time that makes such materials interesting to detect makes them frustratingly small and easily redistributed into broadly homogeneous matrices over geologic time. There is also the possibility that a civilization's own attempts at survival, geoengineering, atmospheric manipulation, large-scale orbital machinery become the final record. Massive orbital systems, if destroyed, could fragment and rain down unusual alloys across the surface in the form of high-velocity bodies that melt on impact, creating localized thermal anomalies and exotic glass types. Atmospheric geoengineering that sought to compensate for climate drift might leave a chemical footprint, persistent halocarbons, odd sulfur cycles, or a sustained spike in atmospheric carbon-2 isotope ratios that would be recorded in carbonate sequences or in the isotopic composition of preserved plant lipids. In short, certain technological activities leave fingerprints that, given the right burial and protection, can be read by sufficiently patient and capable readers. But all signatures degrade. Time is an equalizer. It does not care whose hands shaped the surface. Vitrified glazing can be chemically altered by weathering, radionuclides decay, isotopic anomalies can be masked by later diagenesis. Synthetic organics can polymerize and carbonize. The best preserved messages are those either phenomenal in energy, creating unambiguous, high-temperature phases or isotope systems, or those that were rapidly buried and shielded from surface chemistry. A city swept by flood into a deep delta and entombed in fine laminations might preserve microstructural and chemical detail in a weigh an exposed urban plain will not. Lava tubes in caves, which protect interiors from radiation and wind, become potential vaults for delicate artifacts and biological residues. Detection, in that sense, is a story of instruments and patience as much as of imagination. Remote sensing can map anomalies, global distributions of metal enrichment, thermal anomalies indicative of buried vitrified layers, orbital gravimetry that reveals subsurface mass concentrations out of step with geology. Hyperspectral imaging might find odd mineral assemblages that suggest high-temperature smelting. Radar can locate voids and stratigraphic discontinuities that are difficult to explain by sedimentation alone. Yet none of these tools can by themselves write an incontrovertible history. The decisive testimony usually comes from laboratory analysis of returned or in situ samples, microscopic textures, microstratigraphic context, isotopic ratios at a precision impossible from orbit. That laboratory work itself is a method of translation. The pattern of trace elements, the lattice defects in metallic residues, the chirality of preserved organic molecules, each is a letter in a dead civilization's epigraph. Consider, for instance, an anomalous concentration of non-radioactive refractory alloys spread across a basin. Microscopic analysis might reveal cooling rates inconsistent with natural igneous processes, a microstructure of phases that requires directed metallurgical practice, and trace impurities that match ores unlikely to have been locally available, all of which would argue for mining and transport infrastructure. A thin layer rich in black carbon and condensed soot, synchronous across wide swaths, could indicate planetary-scale burning consistent with industrialized combustion and incendiary warfare. The co-occurrence of these layers with unusual synthetic compounds, complex, halogenated organics not found in natural metabolic pathways, would push plausibility further in the direction of technological causation. But even with perfect preservation, interpretation is fraught. Natural processes are adept at mimicry. Impact events can create glass and melt products that resemble slags. Hydrothermal systems can concentrate metals and produce metallic precipitates that superficially imitate smelting residues. Abiotic synthesis can yield complex organics under the right energy fluxes. Therefore, scientists adopt a posture of skepticism and ensemble evidence. Compelling claims rest on the consistency of multiple independent anomalies that, in concert, are unlikely to be produced by known non-cultural geologic processes. Beyond methods, the morality of unearthing such a story is profound. If a dead civilization's signature were discovered, the reaction would not be merely scientific curiosity, it would be ethical, existential, political. There is a duty of stewardship embedded in the act of excavation, a need to ensure that the act of reading does not itself eradicate the remaining record. Planetary protection principles already formulated for Martian missions take on amplified gravity. The very decision to drill, to sample, to remove, to return, each is a choice that modifies the record in irreversible ways. The modern epistemic apparatus is therefore entangled with preservation, high-resolution remote sensing to minimize invasive intervention, contamination controls to prevent forward contamination from Earth life, and international deliberation on the handling of materials that may be not only culturally significant but potentially biohazardous. The emotional texture of such a discovery is a blend of melancholy and didactic clarity. There is an irreducible sadness in encountering the end of another culture before its full story can be told, a human instinct to mourn the loss of complexity, whether it is microbial ecosystems or monuments of thought. Yet there is also a sober lesson. Worlds change, sometimes abruptly, and the footprints of intelligence can be brittle. The ruins would stand as both mirror and warning. They would show pathways by which habitable states can be lost through impacts, volcanism, runaway greenhouse effects, or the cascading consequences of technologies turned toward destruction. The discovery would force a re-evaluation of resilience, what forms of infrastructure, governance, and planetary management maximize the chance that a civilization's knowledge survives its crises. For the watchers, the calculus is both pragmatic and philosophical. Pragmatically, the find would redirect resources, new missions, new laboratories, new ethical frameworks for handling ancient technology and possibly preserved biology. Philosophically, it would urge humility in claims about the universality of permanence. Civilizations are not guaranteed legacies. Their artifacts are subject to planetary entropy. The memory of a metropolis can survive as glass beads in a delta, as a radionuclide spike in layered clays, as rare alloys in a sedimentary horizon. or it can dissolve into geochemical noise. The existence of one erased civilization would not instantly recalibrate odds about the ubiquity of intelligence in the cosmos. Rather, it would complicate them by showing how easy it is for the material traces of thought to disappear. There is also an epistemic humility in reading absence. A planet may have hosted complex social orders, technologies, and ideas, yet leave little beyond subtle chemical distortions. The absence of unmistakable ruins and remote images is not strong evidence that the planet was never home to organized activity. Conversely, the presence of an anomalous layer requires rigorous cross-examination before invoking intelligence. The interplay of these two inferences, absence is not proof of absence, an anomaly is not automatic proof of agency, defines the methodological posture of any careful investigation of vanished worlds. Lastly, the story returns to Earth in ways that are both intimate and planetary. Recognizing how fragile the record of a civilization can be reframes contemporary debates about legacy and sustainability. If a flourishing, technology-bearing species can be buried by a single epochal event, natural or self-inflicted, the responsibilities of those who come after are stark. To steward a planet is to accept a duty, not just to present life, but to the integrity of the planetary archive. It is to design technologies, institutions, and ethical systems that minimize the risk of irreversible loss. It is also to invest in the patient work of listening to strata, isotopes, and buried glass, so that if a civilization's end finds itself recorded somewhere in the sedimentary memory of the cosmos, the readers who come later can reconstruct the brief, bright duration of life with care. To stand at that interpretive threshold between the living present and the sedimentary silence is to confront a mixture of grief and instruction. A once living planet that has become a tomb is not merely an object of archaeological intrigue, it is a moral parable etched in stone and isotope. The evidence might be a thin, anomalous veneer in a basin thousands of miles wide, a regional, vitrified layer where cities once stood, or a global spike in trace elements and organics that refuses natural explanation. Whatever the form, the lesson is the same. Intelligence alters and accelerates planetary processes, and those alterations can become the instrument of their own erasure. The watchful reader of such a world must therefore be patient, methodical, and ethically exacting. There will be moments of near certainty and long stretches of ambiguity. There will be datasets that glitter with possibility and others that cool into ordinary geology. In the end, whether a planet's silence is due to natural catastrophe or to technological war, the surviving record will be sparse, eloquent, and demanding of humility. If another civilization's last breath is written anywhere, it will be in the chemistry of sediments, the microstructure of glass, the residual isotopes that no wind can carry away. To find and to interpret those signs is to learn not only about another world, but about the precariousness of complexity everywhere, including the one human beings call home. What if a whisper picked up on a dish was not merely the static churn of plasma and dust, but the blurred last syllable of a mind that once lived under a different sky? The image! A faint carrier wave buried inside a cacophony of cosmic noise. A methane puff drifting up through a cracked plane becomes a single provocative hinge. Could these ephemeral phenomena be the echoes of intelligence on a world that time has weathered into silence? That question is not a simple leap into fantasy. It is an invitation to examine the physics of signals, the chemistry of atmospheres, and the ways in which a planet can both keep and lose its stories. The modern record begins with instruments listening and sniffing. Radio telescopes sweep the heavens for narrowband beacons, repeating pulses, artificial modulations, the kinds of electromagnetic fingerprints that, on Earth, betray technologies. Orbiters, landers, and rovers sample atmospheres for trace gases, and among them, methane has long been singled out as chemically interesting. Methane is fragile in planetary terms. In oxidizing, radiation-bathed surfaces, it should be ephemeral. Yet repeated missions returned hints of transient methane, localized spikes, seasonal fluctuations, a pattern that teased both hope and exasperation. The juxtaposition of mysterious radio signatures, sometimes plausible, often ambiguous, and methane's fleeting presence conjured a dual narrative: electromagnetic anomalies on the one hand, and chemical outbursts on the other, two channels of potential testimony from beneath a rust-colored crust. Understanding whether either channel could plausibly be an intelligence's remainder demands a short primer on how signals survive. Electromagnetic transmissions are, by nature, transient. A radio broadcast expands outward at the speed of light, dilutes and fades, absent an engineered storage medium, a satellite, a buried data bank, a mirror habitat, A signal does not leave a long-lived record on the geography of a planet. Thus, the idea of listening for the ghosts of an extinct civilization across geological time is immediately constrained. What can persist for millions or billions of years is not airborne radio, but the durable artifacts and chemical legacies that radio waves cannot preserve. Exceptions exist in thought experiments. An intentionally engineered beacon placed in a stable orbit or a long-lived transmitter shielded from erosion could, in principle, continue broadcasting long after its builders were gone. But planetary processes, micrometeoroid abrasion, and orbital perturbations conspire against such longevity. The more natural inference is that ephemeral radio anomalies are more likely to be contemporary phenomena, either recent human radio interference, natural electromagnetic emissions, or, in the remote possibility imagined here, recent transmissions from some active source. Methane, by contrast, is a chemical residue that can persist and be replenished episodically. Its detection invites a different set of questions. On a planet with an oxidizing surface and a thin atmosphere, methane should be destroyed on relatively short timescales, years, decades, centuries, depending on local chemistry and radiation flux. The discovery of methane spikes therefore implies active production or sudden release from reservoirs. The list of plausible producers is long: subsurface serpentinization, where rock-water interactions liberate hydrogen, and then methane, clathrate destabilization, where methane trapped in icy lattices is released by warming or depressurization, meteoritic delivery of organics, later processed by surface chemistry, and, tantalizingly, biological methanogenesis, microbes metabolizing and producing methane as a byproduct. Distinguishing these pathways is difficult remotely, and the ambiguity invites caution. Methane's presence is an interesting symptom, but not a diagnosis. If the two channels, radio and methane, ever appear to speak at the same time, coincidence alone would not establish interlocution. Correlation merits curiosity, but not conclusion. Consider the kinds of natural radio emissions Mars can generate. Martian dust storms, vast and electrically active, create intense triboelectric charging as particles collide and rub. That charging can produce radio frequency bursts, a kind of planetary static produced by moving sand. Lightning is less likely on Mars than on Jupiter or Earth because of its thin atmosphere, but electrostatic discharges and plasma interactions during dust lifting can produce detectable radio transients. Similarly, tectonic fracturing or sudden outgassing events can generate electromagnetic impulses through piezoelectric and plasma-related processes. In short, natural geophysical events are capable of producing radio signatures that, when filtered through limited data sets and shaped by instrument sensitivity, can resemble artificial modulations. Methane releases and electrostatic phenomena can also be entwined in purely physical ways. If subsurface reservoirs warm, the liberation of gases moving through cracks can mobilize dust, creating local electrification and therefore radio noise concurrent with methane plumes. A geologically active patch could thus present both a radio burst and a chemical exhale without any biological agency. Remote observers, hungry for narrative, can misread such a duet as the chorus of sentience when it is a duet of rock and wind. Yet the possibility that some fraction of the observed signals could reflect deliberate transmission cannot be dismissed entirely. From first principles, techno-signatures need not be narrow-band radio waves beamed intentionally at other worlds. They include a broader taxonomy, repetitive pulse trains, unusual spectral lines from artificial elements or alloys, coherent modulation patterns inconsistent with known natural plasmas, or persistent narrow spectral peaks that are difficult to reconcile with natural thermal or plasma emissions. In principle, if a technological society built infrastructure with energy densities or frequency management techniques foreign to natural processes, those artifacts could appear as anomalies. The challenge is separating those rare, credible signatures from a cacophony of natural phenomena and from terrestrial contamination. Human radial leakage in spacecraft operations complicate the listening environment. An accidental transmission from an Earth instrument can masquerade as extraterrestrial, and the only remedy is meticulous provenance, cross-checking timestamps, antenna patterns, and orbital ephemerides. A further complication lies in timescales. Civilizations that would leave electromagnetic beacons long-lived enough to be discovered by later ears must plan for deep time in ways that terrestrial societies rarely do. Most of humanity's radio heritage in space is ephemeral on geological scales. Satellites decay, plastics embrittle, circuits corrode. A civilization hopeful of transmitting its last word to future epochs would have to invest in materials and architectures designed to resist radiation, thermal cycling, and chemical erosion, or deliberately place their messages beyond planetary vicissitudes. The physics of orbital mechanics, however, limits the options. Orbits decay, micrometeoroid bombardment accumulates damage, the solar wind erodes exposed hardware. To persist for millions of years, an object must be either buried or designed with exceptional redundancy and self-repair, which again leaves physical artifacts rather than airborne signatures. Thus, the conversation shifts from the improbable of ancient radio ghosts to the possible of durable technosignatures locked in matter. If methane pulses are hints of subsurface reservoirs, could those reservoirs also be repositories of engineered materials, metallic components, vitrified slags, or concentrated isotopic anomalies? In that sense, the radio question and the methane question become complementary investigations. One channel, radio, searches for active electromagnetic agency. The other, methane and other trace gases, searches for the metabolic or geologic processes that could indicate habitability or recent activity. Both require multimodal corroboration. A transient radio burst unaccompanied by corroborating spectral, spatial, or stratigraphic anomalies is weak evidence. A methane burst with no co-located mineralogical oddity is suggestive but ambiguous. The strongest case for something unusual is convergence, methane anomalies tied to subsurface structures with unexpected mass signatures, or radial pulses originating from fixed locations associated with materials chemistry that belies natural formation. The practical response to such a possibility has both scientific and ethical dimensions. On the scientific side, the strategy is straightforward: increase resolution, cross-validate across wavelengths and instruments, and preserve context. Orbital radar can probe subsurface layering, looking for voids, sedimentary sequences, and mass anomalies. Hyperspectral imagers can map mineralogy at scales that reveal smelting products or concentrated organics. In situ platforms with drilling and sterilized sampling capabilities can test for isotopic patterns characteristic of biological methane, for example. The fractionation patterns in carbon and hydrogen isotopes are hint at metabolism rather than geology. Radio observatories must coordinate to rule out terrestrial interference and to characterize the emission properties, bandwidth, repetition, polarization. The standard of evidence in such inquiries must rise commensurately with the magnitude of the claim. Ethically, questions proliferate about intervention and contamination, the act of responding to a potential Martian signal, by sending a reply, by directing more invasive probes, by attempting retrieval, risks altering or degrading the very record sought. Planetary protection protocols are not mere arcane bureaucracy. They are a recognition that investigators can damage or mask subtle biosignatures through microbes hitchhiking on hardware, through unsterile sampling, or through the energetic disturbance of excavation. The temptation to act quickly in the face of provocative signals must be balanced against the obligation to preserve. Listening is a form of stewardship. In the presence of ambiguous data, patience and rigor are the moral options. More philosophically, these inquiries confront human imagination with an asymmetry of time. An electromagnetic whisper is contemporaneous. A chemical puff may indicate processes operating over centuries or millennia. A buried artifact points to epochs beyond comprehension. The pleasure of discovery competes with the difficulty of narrative. Suppose a robust technosignature were discovered and dated to 1 million years ago. What would that mean for the human sense of lineage? It would not make other species kin in the genealogical sense, but it would reframe intelligence as a pattern that can emerge and perish within the same planetary geophysical currents that uplift and sink continents. Equally, an entirely abiotic explanation for the signals, one that attributes methane and radio bursts to the interplay of subsurface clathrates and dust storms, would still teach a lesson. Planets are dynamic, and their transient outbursts can be mistaken for intention when listeners are eager. There is, finally, a more practical lesson built into the suspense. Whether the faint carrier waves prove cultural or natural, their detection spurs investment in better instrumentation, more coordinated observation campaigns, and stricter protocols for data provenance. The attempt to resolve ambiguous signals forces a maturation of method. Histories of science are full of near misses that eventually yielded foundational advances precisely because they refused to be satisfied with shallow readings. The same could be said of Mars. The quest to understand transient methane and enigmatic radio noise may, in the end, give humanity a clearer picture of planetary processes, of subsurface hydrology, and of the thresholds of detectability for techno-signatures. If there is an emotional dimension to this investigation, it is a particular blend of modesty and urgency. The dream of hearing a last word from another mind is intoxicating. The reality is stubbornly incremental. Each non-detection, each natural explanation that replaces speculation is not merely disappointment, it is information. It tightens confidence intervals, narrows hypotheses, and refines instruments. The planet's apparent silence teaches a kind of humility, that the universe does not yield its secrets to wishful thinking, and that the signals most worthy of belief are those that survive the gauntlet of cross-disciplinary scrutiny. And yet, even in silence, there is invitation. A transient burst, a methane plume, an odd radar echo, each is an entrance into a deeper investigation of time, chemistry, and durability. They are not necessarily the voices of a sentient past, but they are messages nonetheless, about the volatility of planetary environments, about the pathways through which habitability waxes and wanes, and about what is required for a civilization to leave durable testimony. Listening to them is both a scientific act and an ethical choice, a covenant to interpret with care, to probe with restraint, and to accept that some answers will arrive only after long waits measured in the patient units of geology. In the end, the possibility that radio hums and methane sighs are the last echoes of intelligence on Mars is seductive and plausible only in carefully delimited ways. Electromagnetic transmissions decay, gases do not last, artifacts can be buried and altered beyond recognition. The sensible response is not to leap into broadcast and counter-broadcast, but to sharpen listening, refine spectral sensitivity, coordinate observations across continents and orbits, drill with sterilized instruments, and treat every anomaly as a set of interlocking hypotheses to be tested rather than a story to be told. To search itself, methodical, skeptical, and ethically constrained, may be the clearest testimony to the very intelligence that imagination longs to find. It is a demonstration that listening well in the long, slow arc of planetary time is sometimes the closest thing to speaking across the ages. What is the weight of a memory carried across continents and millennia when disparate peoples, separated by oceans, languages, and technologies, find themselves composing remarkably similar myths about gods from Mars? The resonance invites two very different responses. One is the patient historian's shrug, patterns of projection and shared cognitive architecture, a human tendency to read intention into the skies. The other is the more provocative thought, that these shared stories might be more than mere coincidence, faint, culturally refracted echoes of a real contact, an event that lodged itself in oral lore, ritual calendars, and stone. The question sits between anthropology and cosmology like a hinge, opening a room filled with both skepticism and longing. Across the ancient world, Mars occupied a special place in the human imagination. Its peculiar color and deliberate motion made it a celestial character. In Mesopotamia, a red star was associated with Nergal, a god of plague and war. In Egypt, the red frenzy of Seth. In the Greco-Roman world, Ares and Mars carried martial connotations. In South Asia, Mangala was an auspicious and troubling presence in the astrological charts. These deities shared a temper. Mars signified conflict, fever, a dangerous vitality. That convergence has a straightforward explanation in astronomy. Mars is one of the brightest wanderers in the sky. Its red hue is striking against the night. When celestial objects stand out, cultures notice and fold them into cosmology. But brightness alone does not account for the striking recurrence of more specific motifs, messengers from the heavens, metal gifts, instructions in agriculture or architecture, or catastrophic omens tied to a crimson light. Those motifs draw attention because they suggest a narrative shape, a story whose elements recur with unnerving consistency. To understand how such motifs might travel and transform, it helps to imagine the mechanics of cultural memory. Oral transmission is not a fragile thread but a braided rope. Songs, rituals, and mythic narratives can persist for thousands of years under the right social conditions. Sacred calendars preserve celestial observations, ritual recountings codify images, iconography gives myths a durable visual grammar. Crucially, memory is not literal. It is interpretive, adaptive, and porous to later meanings. A meteor event could be reinterpreted as a divine visit. A bright conjunction might be woven into kingship myth. Over centuries, such stories condense and re-expand, integrating local concerns. The notion of gods from Mars could thus be a palimpsest, a record overwritten many times, its original ink faint but detectable in recurrent strokes. There are, however, additional mechanics that make these myths especially interesting. Human minds favor agency. The evolutionary development of hyperactive agent detection meant that seeing purposeful movement in the sky was more than memorable, it was consequential, an object that moves predictably yet differently from the stars. Bright, red, occasionally conspicuous for its motion, inspires narratives that name intention. Tribal cosmologies, royal propaganda, and priestly orders all co-opt such images to legitimate actions, interpret misfortune, or organize seasonal activity. The effect is to institutionalize celestial myths. What begins as an observation becomes ritual, and what becomes ritual becomes a conservator of memory. Over millennia, the original causal event recedes into metaphor, but the myth survives, rearticulated with each generation's anxieties and hopes. From the perspective of an investigator standing at the interface of archaeology and planetary science, the question becomes empirical. Could any physical trace of a Martian visit plausibly integrate into the archaeological and geological record on Earth? Meteorites from Mars do land on Earth. That much is indisputable. They are tangible testimonies that material exchange between planets happens. The famed ALH 82001 meteorite, with its tiny mineral and carbon anomalies, became a public test case for how Earth and Mars share material history. It prompted fervid speculation about microbial fossils and about the ways rocks can carry the chemical whispers of another world. Meteorites do not, however, speak. They carry raw material, not instruction manuals. Their arrival on Earth could inspire myth, certainly, but a rock that fell and burned into a crater is not the same as a being who taught irrigators where to dig or architects how to place stones. If a civilization from Mars had reached Earth, what form would its imprint have taken? The most durable traces of any contact would be material, non-terrestrial alloys, isotopic anomalies, vitrified deposits with cooling histories inconsistent with natural processes, or sudden appearances of technologies that leave chemical legacies. But Earth is a noisy archive. Geological and biological processes obliterate, rework, and redistribute foreign material. Even a striking anomaly can have geological cousins. Impact melt can look like smelting slag. Hydrothermal mineralization can mimic metallurgical concentration. These proximate natural explanations are the reason scientists demand rigorous, multi-proxy evidence. Extraordinary claims require convergent lines, isotopic ratios inconsistent with local geology, metallurgical microstructures that cannot be produced through known volcanic or impact processes, and stratigraphic contexts that situate anomalous materials within a coherent temporal framework. Beyond material traces, myth itself can be part of the evidentiary fabric, but with extreme caution. Comparative mythology can reveal motifs that do not readily arise through independent invention. When similar stories cluster in cultures without known contact, scholars examine whether these patterns reflect a shared human cognitive toolkit, convergent socio-cultural evolution, or an astonishing historical link. The mathematics of transmission matters. How likely is it, statistically, for independent cultures to generate near-identical narrative sequences about metal gifts, aerial chariots, or star-born teachers? The answer depends on both cultural ecology and psychological proclivities. Weapons, for instance, are universally salient, and a red planet linked to war might naturally prompt an association with arms or strategy. But more idiosyncratic motifs, complex astronomical calendars keyed to Martian cycles, repeated motifs of a particular emblem across distant regions, or sudden synchronous technological leaps would be harder to explain as independent invention. There is also the time depth problem. Human written records reach back several thousand years at most. Oral traditions can stretch farther, but become increasingly fluid with age. Mars's most habitable early eras were billions of years ago. If there were visitors in the relatively recent Holocene, within the time frame of human civilization, the memory could, in principle, persist culturally. If the temptation is to anchor myth in astronomical contact within the last few millennia, the geological context of Mars complicates the story. The planetary processes that make Mars interesting for paleohabitability are wet Noachian valley formations. Potential subsurface refuges date to a time before complex human life. The mismatch of timescales reduces the prior probability that a technological Martian civilization and human cultures overlapped. That is not a definitive refutation. It is a probabilistic restraint. Science must weigh the low prior probability against any anomalous data that would increase posterior plausibility. Another physical mechanism that invites curiosity is the exchange of biological or chemical material by meteorites. Mars' ejected rocks have reached Earth. Could they have carried microbes or some biochemical catalyst that influenced terrestrial life or made certain events memorable? The panspermia hypothesis explores such cross-planetary fertilization scenarios. If Mars harbored life that hitchhiked to Earth, then myths of visitors could be cultural exegesis of a real biological encounter, a misreading through human narrative forms of a fundamental interplanetary exchange. Again, such a claim requires evidence in paleobiochemistry, molecular fossils, trace element patterns, isotopic fractionations in ancient sediments that cannot be easily produced by terrestrial processes alone. Beyond the strictly empirical, there is the psychology of longing to consider. The recurring image of a red god descending from the sky carries a profound emotional charge. It expresses human yearnings for authority, for external origin stories that explain suffering and fortune. The motif of a culture learning tools, agriculture, or social organization from a celestial teacher is a narrative convenience. It resolves the chaotic uncertainty of invention into a linear, comprehensible gift. In modern guises, the same yearning animates speculative documentaries, pseudoscientific texts, and the cultural fascination with ancient astronauts. The pattern is not proof of contact, it is proof of desire. That desire drives interpretations, fuels confirmation bias, and shapes the reception of ambiguous data. The scholarly responsibility, therefore, is to separate what the data can support from what the imagination wants to believe. Interdisciplinarity is the compass for that separation. When mythologists, archaeologists, planetary scientists, geochemists, and statisticians converge, the analysis gains robustness. Archaeology can identify anomalous artifacts or stratigraphic disruptions. Geochemistry can trace provenance and thermal histories. Archaeology of religion can chart the morphology and transmission pathways of motifs. Astrophysics can calculate the plausibility of interplanetary travel within relevant epochs. Together they form a lattice that can hold or reject the hypothesis of actual contact. The goal is not to snuff imagination, but to replace seductive narratives with testable, falsifiable models. There is, too, an ethical dimension to the inquiry. The way modern observers interpret ancient myths shapes policy and cultural attitudes. Labeling a myth. Evidence of extraterrestrial contact elevates certain narratives and can marginalize indigenous explanatory frameworks. It appropriates sacred stories into a scientific drama in ways that can be insensitive or reductive. Respect for cultural traditions requires that scientific curiosity not become a vector of erasure or sensationalism. The responsibility is to listen with humility, to enrich understanding without colonizing the symbolic worlds that these myths sustain. And yet, there is a poignantly human reason to keep the question alive. These myths, whether coincidence, cultural projection, or faint memory, have power. They animate the desire to explore, to send instruments across space, to return to the night with new questions. The notion that other intelligences might have once touched the same cosmic stage reframes Earth's place in the universe not as a solitary island, but as part of a potentially broader narrative of minds arising and vanishing. The idea is sobering. If a contact event did occur and left no durable material trace, its cultural aftershocks would nevertheless have shaped ceremonies, calendars, and moral imaginations. Similarly, if the narratives are purely human inventions, they remain instructive. They reveal how societies negotiate the unknown, encode anxieties, and anchor identity to the sky. In practical terms, the search for a testable connection between Martian matter and terrestrial myth proceeds on multiple fronts. Archaeologists continue to scrutinize anomalous sites with a cautious eye for non-local materials or production techniques that exceed local technological baselines. Geochemists probe sediments for isotopic anomalies that cannot be reconciled with known earthly processes. Planetary scientists refine orbital maps of Mars to identify the most plausible preservation context for any ancient artifacts, deltas, burial troughs, lava tubes, and then model plausible transfer mechanisms for material between worlds. Comparative mythologists map motif distribution statistically, seeking patterns whose probability under models of independent invention is low. The convergence of a material anomaly with a coincident cultural motif in a temporally constrained horizon would alter the conversation. Until then, the hypothesis remains an intriguing, high-risk proposition. At its best, This line of inquiry demonstrates scientific discipline and cultural humility in equal measure. It recognizes the catalytic role myths play in motivating exploration without granting them the evidentiary status reserved for samples, isotopes, and stratigraphic sequences. It treats human narratives as data, rich, meaningful data, but data that require context, triangulation, and critical interpretation. It understands that a myth's endurance does not confirm literal truth, but does indicate a persistent cognitive and social pattern, worthy of study in its own right. Ultimately, the question of whether the shared stories of gods from Mars are coincidence or faint memory is not merely a paleocontact hypothesis to be verified or refuted. It is a test of how humans balance wonder with method. The myths are mirrors. They reflect the mind's appetite for origin narratives and the ethical contours of cultural memory. Whether those mirrors reveal a true historical contact or show only our species' propensity to gift the sky with intention, they remain part of the human archive, a memory of Earth that is partly factual and partly poetic. That archive will be read with increasing rigor. New instruments will specify mineralogical outliers. Refined radiometric techniques will constrain ages with greater precision. Databases of mythic motifs will grow more comprehensive and computationally analyzable. Each advance narrows the range of plausible interpretations. The most likely outcome is incremental, a gradual tightening of probabilities rather than a single dramatic revelation. Even so, the implications are profound. If evidence ever accumulates in favor of contact, the narrative of human uniqueness will shift. If it does not, the persistence of the myth becomes a compelling subject in its own right, a window into the human mind that sought companions in a cosmos long before it had the means to reach them. In the meantime, the question endures as a kind of ethical and intellectual engine. It keeps attention trained on careful excavation, scrupulous analysis, and respectful engagement with ancient cultures. It demands that scientists and storytellers alike separate what can be asserted with confidence from what must remain speculative. And it does something else. It preserves wonder, to wonder that the same red point of light could have inspired gods, omens, and awe across continents is to admit a vulnerability and grandeur in the human condition, a readiness to see meaning in the night, and to ask the long, patient questions that science is best equipped to answer. Whether those investigations eventually confirm a deep memory of visitors from Mars or reveal only the extraordinary inventiveness of human imagination, the labor itself teaches humility about time, evidence, and the fragile ways in which stories and stones keep the memory of a planet. 9. Buried technology. What would a technology look like after a billion years of indifferent geology? The question reshapes itself from imagination into a series of pragmatic tests. What materials endure, how burial alters chemistry, and which instruments can read a story that has been overwritten and smudged by time. The image of a tool, a machine, a city reduced to a mineralogical footnote is at once melancholic and instructive. It forces the inquirer to translate the language of artifacts into the language of sediments, to learn how to read manufacture as a variant of geologic process. The first, and perhaps most essential, realization is material durability. Not everything humans make is meant to last. Organic polymers fragment under ionizing radiation. Biological tissues fossilize only under very particular conditions, even many. Metals oxidize into near indistinguishable ores. The materials most likely to survive are those already favored by natural geology, refractory ceramics, fused glass, certain high-temperature alloys, and large masses of worked stone. Vitrified slag, the glassy byproduct of smelting, is a particularly good candidate. Under rapid burial, it can be protected from surface oxidants and radiation. Its microtextures, quenched droplets, bubble alignment, crystalline inclusions, record cooling histories unlike those of impact glass or volcanic obsidian. In short, the microstructure of a sample is a time capsule, registering whether heat was applied in controlled furnaces or released in chaotic cosmic impacts. Burial is the planet's archivist. Rapid sedimentation, a delta flood, a crater lake infill. An ash fall acts like sealed pages being tacked onto a book. Jezero's delta, a frequently discussed target, exemplifies why deltas matter. They lay down fine-grained, sequential laminations that can trap and isolate organics and particulate debris. Within such laminations, delicate microstructures survive, soot-like residues, microbe-like morphologies, and perhaps residues of processed materials. A vast, slow-moving river that dumps its load into a standing body of water is literally a memory machine. Each layer records a moment of deposition where a technogenic deposit existed at the time of burial. Its signature could be fossilized in place. Subsurface vaults, lava tubes, cave networks, and deeply buried aquifers offer a different kind of preservation. They are shielded from the surface chemistry that pulverizes and oxidizes. Radiation falls off quickly with depth. Temperature variations moderate. The kinetic violence of wind and micrometeoroid sandblasting is absent. A delicate lattice work of design material might lie in such a vault, hidden beneath hundreds of meters of basalt, intact in a way surface ruins never would be. Radar sounders that return layered reflectivity or void-like echoes are, in such contexts, archaeological probes. A pattern of consistent, rectilinear reflectors under a delta or a basalt sheet stirs attention precisely because most natural. Stratigraphy resists repeating orthogonality at scale. Detection follows a choreography of modalities. Gravity anomalies flag mass concentrations. Magnetometers identify thermal histories in remnant fabrics. High-temperature smelting demagnetizes or remagnetizes rocks in patterns that differ from background geology. Hyperspectral sensors map mineralogy with a precision that can separate a clay from a vitrified slag or a carbonate from a fused industrial silicate. Ground-penetrating radar and orbital sounders reveal layering and voids. Each dataset is a dialect. Only when they speak together can a coherent thesis emerge. The interpretive challenge is conservatively simple. Natural processes can imitate manufacture. Columnar jointing, cooling dikes, and fracture networks produce orthogonal patterns. Hydrothermal deposits can concentrate metals and form glassy textures under rapid heating and quenching. Impact melt can produce glass indistinguishable at first glance from material produced by furnaces. The scientific standard, therefore, demands ensembles of evidence, geometry plus chemistry plus stratigraphy plus isotopic marks. A single anomalous shard on a plane's image is not enough. A swath of vitrified strata, spatially bounded and coeval with a depositional event, layered above and below with undisturbed sediments, is the kind of pattern that begins to speak in a different register. Isotopes are the detective's shorthand. Industrial processes fractionate isotopes in ways that many natural processes do not. Large-scale metallurgical extraction leaves trace element gradients and isotopic ratios in slags and tailings that differ from crustal averages. Combined with mineral microstructures indicative of directed cooling or alloy formation, isotopic anomalies can be the clearest line separating craft from chance. In these cases, return samples become decisive. Laboratory instruments, secondary ion mass spectrometers, transmission electron microscopes, nanoscale X-ray diffraction can reveal cooling rates and trace element partitions that are near impossible to confuse with. Volcanism or impact melt. Scale, too, is a crucial variable. Small artifacts vanish more easily than large infrastructural signatures. Massive earthworks, quarry scars, anomalous terracing, and altered drainage basins would leave a landscape-scale imprint that persists longer. An economy of extraction. Open-pit mines, slag fields stretching over kilometers, terraces cut into bedrock, will disturb sediment budgets, change depositional gradients, and create mass-balanced signatures measurable by orbital gravimetry. Such macro signatures are easier to separate from background geology, provided they cohere spatially and are corroborated by mineralogical oddities. Yet the more robust the artifact, the more likely it is to have been repurposed by geology. Weathering, percolating groundwater, and later tectonic activity can redistribute concentrated materials. Metals migrate into new phases, glass devitrifies and becomes crystalline over time, carbonaceous residues oxidize or are converted into kerogens. Even a robust industrial horizon can be reworked into a faint chemical veneer that only high precision geochemistry can distinguish. The search, therefore, is a patient, probabilistic hunt. Instruments look for the most conserved signals, thermally altered phases, non-equilibrium alloys, isotopic excursions, and coherent mass anomalies. There is also an ethical dimension that weighs as heavily as the technical one. To open a subsurface archive is to alter it irrevocably. Planetary protection is not an abstract constraint. It is a moral principle predicated on leaving a record unspoiled for future readers. The drive to drill and to return samples must be balanced against the duty to preserve context. Sterilization protocols, non-invasive first-pass surveys, and incremental sampling strategies become not merely engineering problems, but ethical decisions. The history of science is replete with examples where early penetration destroyed the very evidence later sought. On Mars, the risk is amplified. The planet's record is both precious and precarious. The more intrusive the intervention, the higher the obligation to justify it with a constellation of remote sensing priors. If buried technologies exist, they are likely to be paradoxically humble in their detectability, not gleaming monoliths standing defiant against time, but faint chemical footprints in a lake bed, not perfect statues, but vitrified residues in a stratigraphic lens. The archaeological imagination must therefore be inverted rather than looking for monuments. It must read chemistry rather than expecting ruins to shout from orbital frames. It must listen for whispers in isotopic ratios and layered quiet. That inversion is also an ethical act. It privileges slow, careful science over sensational claims. Finally, the very possibility of buried technology reframes human purpose. The search for technogenic residue is not solely a hunt for companionship in the cosmos. It is a meditation on fragility. If advanced manufacture could be buried and erased on a planet that once supported flowing water and thicker air, then the permanence of human artifacts is also in question. The act of searching thus doubles as a lesson in stewardship. The same processes that conceal extraterrestrial craft can erase human legacy. To learn how to preserve or to leave intelligible testimony across deep time becomes part of the same project that seeks to decipher what may already be buried. 10. The rules of the cosmic game. If there are patterns governing the rise and fall of civilizations beyond Earth, they will be less mythic laws and more physical constraints, the kind of background rules that make certain strategies viable and others impossible. Those rules are not moral imperatives, they are thermodynamic, astrophysical, and probabilistic realities that shape any intelligence's options. To call them laws of the cosmos is to admit that life and technology must obey the same arithmetic as stars, planets, and entropy. Energy is the primary currency. Any society that aspires to global engineering, long-term orbital platforms, or interplanetary voyaging must master sources of energetic power that scale beyond local muscle and biomass. On a planetary surface, the leading contenders are stellar flux, chemical gradients, and geothermal heat. The Kardashev scale gives a heuristic. Civilizations are measured by the fraction of a star's energy they harness. But the scale is not destiny. Photovoltaics, nuclear fission, and fusion each come with engineering and ecological constraints. Collecting a significant fraction of a star's output implies megastructures or massively distributed systems, each of which is vulnerable to wear, cascading failure, and maintenance costs that compound over centuries and millennia. Thermodynamics also enforces limits. Any process that computes, that moves mass, that maintains ecological stability produces waste heat. In closed environments, that waste accumulates and must be radiated away. As a civilization's energetic throughput increases, managing entropy becomes not a side problem, but the central engineering challenge. Planetary climates can be sensitive to even modest changes in albedo or greenhouse gas concentration. Geoengineering at planetary scale can create temporary reprieve, but also accidentally trigger runaway feedbacks. In this sense, the laws are blunt. Entropy accumulates, heat must be shed. Closed biospheres require buffers that are non-trivial to design and maintain. Information flow defines detectability. A society that emits broad-spectrum radio, that alters its planetary atmosphere, or that builds large, coherent structures is making itself legible. The converse is also true. Stealth is achievable by reducing waste emissions, thermal, electromagnetic, or chemical. This trade-off underpins many solutions to the Fermi question. Civilizations that maximize longevity may minimize detectability, while those that are noisy may be transient. The probabilistic implication is sobering. If the cosmos is populated with technical societies, many will either be faint or ephemeral. Time complicates everything. The characteristic timescales of stellar and planetary processes, millions to billions of years, dwarf the lifespans of technological epochs measured in centuries. The window in which a civilization both exists and emits detectable technosignatures that survive long enough to be observed is narrow. This temporal narrowness multiplies the difficulties of contact, bursts of radio emission, atmospheric pollution. All cultural artifacts are ephemeral. To make a durable mark across deep time requires deliberate design, durable materials, burial strategies, or active maintenance over geological epochs. Absent intentionality toward deep time preservation, the material traces of even advanced societies fade into the geological background. Self-limiting dynamics, ecological overshoot, resource depletion, social destabilization. are not metaphysical curses, but plausible outcomes of unchecked growth within finite planetary systems. The great filter concept frames one interpretation. Somewhere between simple chemistry and galaxy-spanning intelligence lies a bottleneck. The filter could be behind us. Life to intelligence is rare. In front of us, intelligent life tends to extinguish itself, or distribute it across many stages. Physics suggests mechanisms for front-loaded filters, runaway greenhouse effects, atmospheric collapse, or cascading ecological failures triggered by energy mismanagement. The historical silence is compatible with these mechanisms without requiring metaphysical silence. It simply requires rare combinations of habitability, technological prudence, and luck. Interstellar distances codify conservatism. The speed of light limit makes direct contact expensive in energetic and opportunity terms. Building probes or beacons intended to span centuries and millennia is a different political and cultural project than launching a generation spacecraft. The economics of information, discounting future value, the cost of construction, the risk of mission failure favor localized investment. Civilizations may therefore prioritize resilience within their star systems rather than cosmic annunciation. From an observational vantage point, that logic produces an asymmetry. The loudest civilizations to detect are those that either intend to be loud or those whose noise is so large that it cannot be contained by prudence. There are emergent behavioral rules gleaned from planetary history and theoretical ecology. Diversity increases resilience, robust feedbacks, redundancy of nutrient cycles, and decentralized infrastructures buffer shocks. Technological societies that embed ecological wisdom into their engineering designs, valuing closed-loop recycling, low-entropy processes, and distributed maintenance, theoretically increase their chance of surviving planetary experiments. Conversely, societies that externalize entropy, dumping waste heat, removing biodiversity, concentrating resource extraction, magnify systemic failure modes. These are not new moral precepts. They are engineering axioms translated into survival calculus. A subtler rule arises from information theory. Complexity begets fragility unless accompanied by modularity. Large, tightly coupled systems can collapse catastrophically under local perturbations. Modular design, with repairable components and local autonomy, improves long-term viability. Thus, the architecture of a civilization matters. Distributed networks with local self-sufficiency will tend to outlast highly centralized megastructures whose failure pathways cascade uncontrollably. Observation imposes its own law, selection bias. The set of civilizations humans can detect is constrained by human methods and sensitivities. Radio surveys are sensitive to certain frequency bands and temporal strategies. Atmospheric remote sensing detects particular molecules at certain abundances. Gravimetry locates mass anomalies of specific magnitudes. The search thus samples a tiny subspace of possible technosignatures. That selection bias invites humility. The silence of surveys is not null evidence for absence, only evidence of mismatch between what is being searched for and what might exist. Another cosmological constraint is the weaponization of technology. High-energy processes that civilizational-scale projects require can also be repurposed destructively. Nuclear fission, engineered biological agents, and climate-altering interventions have the dual-use problem. They enable both survival and self-termination. Societies that solve the coordination problem, the governance that restrains dangerous options until mitigations exist, are more likely to demonstrate longevity. Governance is therefore as much a physical constraint as metallurgy or energy. The capacity to manage risk collectively across generations is a meta-rule in the cosmic game. Finally, reciprocity between detection and preservation emerges as an ethical law. The very act of seeking can be destabilizing. A probe that lands and drills can contaminate. A broadcast can attract attention that a civilization is ill prepared for. The scientific community's rules for planetary protection are not arbitrary. They are expressions of a principle that discovery should not be purchased at the cost of erasing what one seeks. In some ways, civilization's maturity might be measured by its ability to explore without colonizing the memory of others. These constraints together produce an interpretive framework for the silence and for the occasional anomalies. They do not prove solitude. They sketch plausible pathways for why technology, even when common, need not announce itself across interstellar distances or remain legible across deep time. Civilization is a physical process subject to thermodynamics, material limits, and cognitive biases. The cosmic game is not winnable by brute force. It rewards prudence, modularity, and an understanding of planetary scale consequences. What follows for humanity is practical and existential. Practically, it suggests priorities for search and stewardship. Detection strategies should diversify, not only radio and optical beacons, but also deep drilling, precise isotopic mapping, and searches for thermodynamically anomalous materials. Preservation strategies should be integral to exploration, sterile sampling, minimal impact landing, and the development of archival practices designed to survive geological epochs. Ethically, the laws imply responsibilities to avoid accelerating planetary failure, to design technologies cognizant of entropy and feedback, and to build governance that can manage the long-term consequences of powerful capabilities. There is a final, quieter lesson embedded in these cosmic rules. Smallness and patience are virtues. The universe is patient in ways human social life is often not. Civilizations that accept the scale of geological and astrophysical time, that plan for maintenance across centuries rather than headlines, that value redundancy over spectacle, stand the best chance of leaving coherent, legible traces. The cosmos offers no conspiratorial silence. It offers a harsh arithmetic. The human task is to learn that arithmetic, to design within it, and to explore with humility. In that humility lies a kind of hope. If the rules favor restraint and sustainable practice, then the silence might be a lullaby of prudence rather than an indictment of loneliness. If the rules instead reveal a universe where most technologies collapse or are erased, then the act of searching becomes a form of memorial, a careful, reverent cataloging of what persistence is possible. Either way, understanding the rules changes behavior. It reshapes exploration from a romance of instant discovery into a long, disciplined effort to read strata, to listen with calibrated instruments, and to leave the smallest possible footprint on the fragile archives of other worlds. The cosmos does not promise companionship. It does offer a set of constraints. Interpreting them well may be humanity's best way to remain in the game. What stops a species that has learned to read the heavens from continuing to exist? That question sits like an urgent pulse beneath every investigation of vanished worlds. It asks less about single catastrophes than about the fragile architectures that sustain complexity, energy flows, planetary envelopes, social contracts, and the long arithmetic of maintenance. Mars offers a hypothetical answer in negative form, a world that, through a suite of planetary processes, lost the conditions that allow surface habitability. For humanity, the same catalogue of vulnerabilities maps onto the present and the future. The threats to humankind are not mysteries. They are a collection of interacting limits, each amplified by scale and speed, each with the power to convert an industrious civilization into an archaeological silence. The first threat is the planet itself. Earth is not a static state, but a set of coupled dynamic systems. Atmosphere, hydrosphere, cryosphere, lithosphere, biosphere. They exchange heat, mass, and chemistry across scales. Human industry has become a new driver within those systems, and the consequences are not linear. Small perturbations can produce thresholds. The image of tipping points is not a poetic exaggeration, but a technical shorthand. The gradual loss of Arctic sea ice that alters jet streams, the dieback of tropical forest that flips a carbon sink into a source, the acidification of oceans that dissolves foundational food webs. These are not isolated failures. They are changes that reorganize planetary feedback loops, potentially ushering in states of climate and ecology markedly different from those under which agriculture, cities, and many technologies developed. Mars serves here as a counterfactual lesson. There, a die-off of atmospheric density produced conditions in which liquid water became ephemeral and radiation exposure intensified. On Earth, a different set of processes, greenhouse forcing, aerosol changes, and land use shifts could drive transitions that are equally transformative. The danger is not simply environmental degradation in aggregate, but the nonlinearity of those changes. Civilizations are engineered for a range of variability. When the environment moves outside that range, infrastructures break, energy grids destabilize, supply chains jam, harvests fail. The peril lies in interdependence. Modern systems are tightly coupled. A failure in one region can ripple globally through trade, finance, and communications. A planetary-scale perturbation becomes not just an ecological catastrophe, but a social one. Second, there is energy and entropy. High technology depends on continuous streams of low-entropy resources, concentrated fossil fuels, fissionable isotopes, high-grade ores, accessible freshwater. The Kardashev-inspired view that civilizations scale with their command of energy is useful, but it is also unforgiving. Harvesting increasing amounts of energy produces waste heat and requires materials that are mined, processed, and transported. Resource extraction is not merely a technical act, it reconfigures landscapes, biogeochemical cycles, and political economies. The story of resource exhaustion is not inevitable, but it is real. High-quality ores become depleted, and extraction moves to lower-grade deposits with higher energetic and environmental costs. Without adequate governance, substitution, and recycling at planetary scale, the energetic base of civilization becomes more fragile, not more secure. Third, the social fabric that binds complex societies is itself brittle when stressed. Civilization rests on trust, in institutions that provide rule of law, in markets that allocate resources, in knowledge systems that transmit skills across generations. Under acute stress, food shortages, mass migration, economic collapse, the bonds of cooperation can fragment. History offers examples in miniature, and speculative scenarios scale those examples up. The possibility of cascading failure looms. Political fragmentation undermines coordinated responses to environmental threats. Conflict disrupts technological maintenance. Weakened public goods erode the ability to manage common pool resources. The most dangerous dynamics are feedback loops that accelerate collapse. Conflict begetting scarcity. Scarcity begetting social collapse. Collapse multiplying the conditions for further conflict. These are not science fiction tropes. They are plausible pathways recognized by social scientists and systems modelers. Fourth, technological risk. Humans create technologies that wield unprecedented powers on planetary scales, engineered pathogens, nuclear arsenals, autonomous systems with emergent behavior, and industrial processes with the capacity to alter atmospheres. Each of these technologies carries a dual-use problem. The same catalytic advances that enable prosperity can, under certain circumstances, become vectors of rapid, large-scale harm. The danger is compounded by a mismatch between technical capability and governance maturity. Institutions that evolved in earlier eras struggle to regulate technologies that are global in effect and that diffuse across borders rapidly. The potentially catastrophic events range from accidental release of engineered biological agents to deliberate deployment of climate-altering interventions without global consent. The material traces of such events would be different from purely natural catastrophes, but the social consequences, breakdown, migration, famine, could be similar or worse. Fifth, the slow erosion of knowledge and maintenance. Complex systems do not maintain themselves by inertia. They require continual care. Cities need water treatment plants. Nuclear reactors need continual operation and supervision. Satellites require station keeping, and digital infrastructure needs patching and secure stewardship. The risk here is not a single disaster, but attrition over long timescales. Institutional memory fades, maintenance regimes falter, technical skills atrophy, and supply chains for critical components become fragile. The archaeological record of a collapsed civilization is often a record of neglected upkeep as much as of cataclysm. The lesson is subtle and unsettling. Surviving a single crisis does not guarantee continuity if the routine labor that sustains. Civilization erodes. Sixth, planetary contamination and the fraught ethics of interplanetary exchange. Explorations of Mars and speculations about ancient Martian civilizations make clear that contact with other worlds is entangled with responsibility. Forward contamination, the transport of terrestrial microbes to an alien environment, can confound the search for indigenous life and permanently alter ecosystems. Backward contamination, the return of alien biological material to Earth, represents a notional risk that commands extreme caution. The scientific drive to know collides with the moral duty to preserve. The decision to send probes, to sample, to return, is a choice that must weigh curiosity against the irreversible alteration of both local and planetary conditions. The wrong choice could imperil not just pure science, but biospheric integrity. Seventh, the probabilistic tyranny of deep time. The passage of millions and billions of years is the great eraser. Structures that seem durable at human timescales can be vanished by long-term geology, climate cycling, or cosmic impacts. For a civilization to leave legible traces across deep time requires intentionality and design choices that prioritize durability, materials selected for endurance, burial strategies, and redundancy. Absent that foresight, even a highly advanced civilization may leave only subtle chemical aberrations and isotopic glitches, inscrutable without the tools of careful geology and geochemistry. The Martian thought experiment shows that exit does not necessarily require annihilation as a single event. It can be a slow, inexorable attrition that reduces the visible archive to ambiguity. Eighth, the politics of foresight. Preparing for existential threats is a political act as much as a technical one. It requires long-term institutions capable of transcending electoral cycles and parochial interests. Yet political systems often discount the distant future. Incentives favor short-term gain. Collective action problems, the tension between private incentives and public goods, hinder effective solutions. Climate change illustrates this problem with brutal clarity. The structural impediments to coordinated, sustained global action are not mysterious. They are a function of inequality, divergent national interests, and competing visions of development. Avoiding large-scale jeopardy demands governance innovations, durable risk pooling mechanisms, enforceable international norms, and institutions that internalize long-term externalities. Ninth, the cognitive biases that impede rational action. Humans evolved heuristics that are excellent for immediate survival but poorly suited to assessing low-probability, high-consequence events. Optimism, bias, myopia, and motivated reasoning distort collective risk assessment. Societies under stress can prefer narratives of denial or distraction, which postpone necessary but costly interventions. The information environment can amplify these biases. Disinformation campaigns, fragmented media ecosystems, and the incentives of attention capitalism can all divert public discourse away from the slow, technical work of mitigation. Finally, the existential uncertainty of being an information processing species in an indifferent cosmos. The same logic that frames the search for techno-signatures, the difficulty of leaving durable imprints, the narrow windows of detectability, the thermodynamic constraints, also reframes humanity's future. Persistence beyond planetary bounds is conceptually possible. Off-world settlements, orbital habitats, and interstellar probes all appear in engineering plans. Yet each of these pathways faces the fundamental realities discussed earlier: energy, materials, maintenance, governance, and entropy. Off-world settlement can diversify risk, but also multiplies dependencies. It requires enormous resources, reliable supply lines, and robust social architectures. Clinging to the illusion of a single technological fix, a Mars colony as an insurance policy, without reconciling the deeper social and environmental challenges on Earth, is a risk in itself. What, then, are the sensible countermeasures, and how do they map onto the threats? The first is humility translated into design, to accept that planetary boundaries exist and to engineer within them. That means rigorous resource accounting, circular economies that minimize waste and maximize reuse, and energy strategies that balance scalability with climate stability. The second is redundancy and modularity, not as abstract principles but as operational law. Distributed energy grids, diversified food systems, regional resource autonomy, and modular technological architectures reduce cascade risks. The third is governance for the long term, institutions designed to steward public goods across generations, with enforceable mechanisms for risk sharing and liability. The fourth is precaution and exploration. Planetary protection must be built into mission architectures, not appended as an afterthought. The scientific enterprise should be accompanied by ethical frameworks that preserve the integrity of alien systems and of Earth itself. There is also a cultural dimension, cultivating a public ethic of maintenance, patience, and deferred gratification. Civilization's longevity is as much about values as about engineers. Valuing long-term stewardship, educating for systems thinking, and embedding maintenance into cultural honorifics, celebrating the caregivers, the repairers, the archivists, changes incentives. It reframes good governance as intergenerational conversation rather than episodic politicking. Finally, diversification of narratives about the future matters. The dominant cultural storyline that equates progress with expansion and extraction needs counterweights that valorize resilience and repair. A civilization oriented toward deep preservation will make choices that look less glamorous in the short run, but vastly more prudent over centuries and millennia. The Martian allegory is stark. A planet that once had more clement conditions and then shifted into a state hostile to surface life is a cautionary tale. Mars did not die overnight. It slid out of a habitable niche. Humanity's challenge is to avoid analogous slide through foresight, restraint, and the committed work of sustaining what is already fragile. The final image is not one of doom sealed in inevitability, but of choices readable and reversible in principle. The threats are real, varied, and interacting, yet they are not metaphysical fates. They are engineering and governance problems writ large. The history of life on Earth shows resilience coupled with fragility. Extinction events and recoveries are recorded side by side. If Mars stands as a possible example of what might be lost, then Earth, vibrant, noisy, and alive, is the place where the hard work of avoidance can still be done. The imperative is not merely to extend capabilities, but to extend care, to design with humility, to govern with foresight, and to cultivate the patient stewardship that might prevent humanity from becoming one day an enigmatic whisper in another planet's strata. If Mars was ever a mirror, what did it show humanity about itself? The question arrives not as a single finding, but as a constellation, valley networks that read like sentences, isotopic ratios that tally loss, faint radar echoes that might be vaults, and the image it throws back is unsettling. A planet once capable of harboring water, habitability, even complexity, reduced over eons into a husk of wind-scoured rock and thin atmosphere. That image refracts into a dozen smaller questions about preservation and erasure, about what counts as a legacy, and about the kinds of choices that determine whether a civilization's testimony survives the slow, indifferent machinery of deep time. This concluding act gathers those strands into a single intention: to translate the speculative inquiry about Martian civilization into a practical meditation about Earth's present responsibilities. It is not an argument that Mars did or did not host minds. It is an argument about consequences. Whether Mars preserves the faintest vestige of an intelligent past or remains a planet of geological voice and microbial mystery, the lessons are shared. The ledger of a world is fragile. Its pages can be written quickly and erased even more slowly, and sometimes catastrophically. Humanity's future, insofar as it intends to leave a legacy that will be legible across millennia and geological epochs, depends on understanding how records persist and how they fail. A legacy is not only marble and metal, it is sedimentary and chemical. It is the preservation of intentional signals in matrices that deep time cannot easily rework. Everyday things that cultures produce, ceramics, alloys, texts, biological records, are vulnerable. Radiation breaks polymers, oxidation corrodes metals, micrometeorites and thermal cycling sand corners down to nothing. The most durable items are those the planet already favors: high-temperature glasses, refractory ceramics, certain crystalline phases, and mass-scale reworkings of the landscape. But durability alone is insufficient. Survival requires either scale, monuments so vast that planetary processes cannot easily erase them, or shelter, burial in stable strata, caves, or ice where chemistry and radiation are held at bay. If there is a moral here, it is a double instructive. First, that what is left behind depends more on choices about preservation than on the mere fact of having once existed. Second, that the act of preservation must itself be designed to withstand the geophysical processes that erase memory. For Earth, this is not mere vanity. It is a practical problem with ethical dimensions. There are ways to be remembered and ways to be lost. A species that seeks immortality through monuments and data must reckon with the arithmetic of entropy, geology, and planetary chemistry. The scientific record gives a map of what works and what fails. Deltas and fine lacustrine deposits are effective memory banks. They lay down sequential layers of fine sediments that can trap and isolate organics and particulate debris. Rapid burial in such contexts arrests oxidative chemistry and shields materials from persistent radiation. Subsurface voids like lava tubes and caverns offer vaults where microstructures could survive with their microchemical fingerprints intact. Radar sounders and gravimetry are the tools that point to such places. Isotopic analysis and microstructural studies are the methods that authenticate them. In short, reading deep-time testimony is a cross-disciplinary exercise. Geomorphology and mineralogy set the stage. Geophysics reveals hidden architecture, and laboratory geochemistry reads the inscription. The political and ethical dimension cannot be sidestepped. Planetary protection, the protocols that govern how humanity explores other worlds, is not a bureaucratic hurdle, but a moral obligation. Forward contamination risks erasing the very subtle signatures of indigenous processes. Backward contamination risks introducing alien elements into Earth's living systems. That duty of restraint must inform mission planning in the same way that preservation ethics inform archaeology on Earth. If a preserved record in a Martian delta could teach future observers about the processes of life and collapse, then sending unsterilized hardware across that threshold would be tantamount to writing over the page before anyone has read it. But preservation is not only about protecting other worlds from human footprint, it is about how humanity chooses to leave its own traces. The paradox is stark. the systems that allow modernity, concentrated energy, mass industrial production, global supply chains, also accelerate the processes that can erase its testimony. High energy economies produce waste heat and alter planetary budgets. Industrial extraction disturbs sediments, changes hydrology, and trenches the very substrates where archives might be preserved. The stewardship imperative is therefore twofold: to minimize the damage to the planet's capacity to preserve information and to design archives that will survive the very forces human activity intensifies. What might such a strategy look like in practice? There are technical and institutional pathways that together increase the odds that something human, a message, a catalogue, a record of knowledge, can survive long enough to be discovered by a distant future investigator or another intelligence. Technically, the emphasis is on durable media and protected deposition. Information encoded in high-temperature glassy matrices, vitrified ceramics, or in mineral phases resistant to chemical reordering will stand better than polymeric media. Embedding robust records into stable continental interiors, bound beneath tens to hundreds of meters of sediment or within deep bedrock, will insulate them against surface chemistry and radiation. Multiple redundant caches across geologically distinct locales reduce the risk that a single catastrophic event, volcanic, seismic, or impact, erases everything. Equally important is choosing forms that are legible to analytic techniques that are far future. Civilization is likely to master isotopic anomalies, pattern distributions of refractory phases, and intentionally regular arrangements of mass concentrations that betray artifice after natural processes are modeled away. Institutionally, preservation requires governance that treats long-term stewardship as a core public good. This is a hard political problem. It demands mechanisms for intergenerational decision-making, funding streams that persist over centuries, and legal norms that protect sites of potential deep-time significance. It implies investment in non-invasive survey technologies, restrictions on industrial activity in archaeologically promising basins, and international agreements about the custody and study of returned samples. The technical desiderata, sterile sampling, cached return strategies, and stringent chain of custody procedures must sit within an ethical framework that prioritizes preservation over speed and spectacle. There is also a cultural work to be done. A society oriented toward leaving a coherent legacy must cultivate the values of maintenance, repair, and patience. That is not merely sentimental, it is strategic. The long-term survival of complex systems rests not on heroic acts, but on quotidian labor, water treatment, power reliability, continuity of records, and routine care of infrastructure. Celebrating the work of repairers, archivists, and the long-view bureaucrats is as important for legacy as celebrating the builders of monuments. If Mars teaches anything, it is that grand engineering can be undone by the slow attrition of neglect. The cosmic rules sketched earlier in this series also feed into this conclusion. Energy is currency, entropy is constraint, and time is the merciless judge. To place durable bets for posterity, a civilization must work within those rules, manage energy flows so waste heat does not trigger runaway changes, design modular systems resistant to cascade failures, and adopt materials and strategies that prioritize thermodynamic and chemical stability. There is a moral calculus here as well. The choice to externalize waste and uncertainty to future generations is a form of intertemporal injustice. The obligation is to leave the planetary ledger legible and intact. Practically, this means rethinking emblematic projects that substitute spectacle for durability. An ephemeral beacon in orbit will not outlast 100,000 years of micrometeorite rain and orbital perturbations. A buried archive of vitrified, redundantly distributed records in tectonically stable cratons has a far better chance. So does the deliberate construction of chemical markers. For example, isotopic signatures placed in particular sedimentary horizons designed to be retrieved and read by analytical techniques that persist across deep time. Though such interventions demand rigorous ethical vetting to avoid altering natural archives in ways that confuse future inquiry. At the same time, humility is the necessary posture of any searcher. The absence of a smoking gun on Mars does not prove non-existence. The presence of an anomaly does not instantly confirm crafted origin. Scientific method, hypothesis, prediction, cross-validation, and careful attribution of probability remains the tool that turns curiosity into knowledge. The initial impulse to declare discovery is seductive and human, the discipline to withhold judgment until convergent evidence accumulates is the hallmark of reliable inquiry. That discipline must be sustained not only by peer review and laboratory rigor, but by an ethic that values preservation over sensationalism. There is an emotional register to this conclusion that is not merely rhetorical. Observers feel a kind of melancholic tenderness toward planetary archives, a sense of kinship with vanished possibilities, and a sober responsibility toward the living. That tenderness is productive. It nurtures a conservation ethic that is capable of restraining the appetite for immediate returns in favor of long-term discovery. The watchers who specialize in planetary ruin are not mere romantics, they are custodians. Their work is an act of careful listening and careful restraint. Finally, the question of legacy reframes exploration as stewardship. Humanity's ventures beyond Earth, whether robotic or, someday, human, must be conducted with the awareness that discovery and preservation are two sides of the same coin. The decision to sample should be preceded by the decision to protect. The act of returning a specimen should be governed by protocols that prevent both contamination and cultural capture. The science that seeks to read another world's history must recognize that it is also writing a new history through the practice of access. Preservation and knowledge are entangled. If Mars is a warning, it is not fatalism. The record of a planet's demise, whether natural or self-inflicted, is a teacher that can be read and learned from. Earth's present condition is not destiny. It is a set of choices shaped by institutions, technologies, and values. Those choices can be guided by the slow, patient logic of geology and by a moral commitment to the continuity of knowledge. To preserve a legacy is to accept that posterity will judge the decisions of the present not only by their immediate benefits, but by their effects on the planetary archive. The closing image is modest and precise rather than grand, a vellum of strata layered with care. Each lamination an argument left for a later reader, vitrified shards sealed in a stable basin, a future geochemist's light into another epoch, an international treaty that protects deltas and caverns from intrusive sampling. Until non-invasive surveys have been exhausted and sterilization protocols satisfied. These are not glamorous scenes. They are small, technical, and intensely human acts of attention. They are the kinds of work that give something a chance to survive. Whether Mars was a cradle, a workshop, or a world that never rose beyond chemistry is a question that will be answered or refined by patient science. Whatever the outcome, the more urgent question, the one this final chapter insists upon, is what humanity intends to leave behind and how it will steward the fragile ledger of Earth. If a world can be whittled down to silence, then the preservation of any message requires deliberate humility, multidisciplinary rigor, and a commitment to restraint. The planet is not merely an object to be mined for knowledge, it is an archive to be preserved for readers who may come along after the present music has faded. The choice is clear in its gravity and its modesty. To be remembered is not the same as to shout into the void. It is to inscribe with materials and contexts that the slow fingers of time cannot easily erase. To act otherwise is to risk that, across the deep, indifferent sweep of epochs, the sum of one civilization's questions and answers will collapse into indistinguishable dust. The better, harder path is to build archives and institutions that survive, to govern with a view beyond immediate generations, and to explore other worlds with hands that do not write over what one seeks to read. In that quiet, steady devotion lies the possibility of a legacy that endures as lesson and as gift, not omnipotent, but legible. Not eternal, but long enough for a future mind to say, here was once a thought, here was once a story worth keeping. What if Mars were more than a neighbor, more than a bright ember in the nocturnal map? What if it were a mirror held up to human possibility? That proposition is less an empirical hypothesis than a lens through which to read a dozen overlapping inquiries about how records survive, what civilizations choose to protect, how societies interpret silence, and what ethical obligations follow when a planet becomes both a subject of study and a repository of potential testimony. The idea that secrets of an alien civilization might lie beneath the planet's red sands does not demand faith, it demands deliberation. It asks how humans will look, what they will risk, and how they will answer if the buried pages finally open. The image of buried evidence is visually powerful because it converts absence into potential presence. A desert-smooth sweep conceals strata of sediment, a palimpsest of past climates and chemical states. That hidden ledger is where the most plausible traces would be found, in fine-grained lacustrine laminations, in deltas that once trapped and sheltered organics, in caves and lava tubes that serve as natural vaults. These are the kinds of contexts in which preservation fights most effectively against the erosive instruments of wind, radiation, and cosmic impacts. To imagine a civilization's remains lying there is to imagine a long game of concealment by geology, not an elegant afterlife for monuments. Even as it invites hope, the scenario imposes methodological caution. Paleoscience and planetary exploration are exercises in reconstructive skepticism. Instruments listen, map, and sample. Scientists cross-validate. Hypotheses are weighed against alternative natural mechanisms. The past chapters of this investigation sketched how valley networks, mineral assemblages, and atmospheric isotopes assemble into a story of a Mars that was once wetter and warmer. Those same datasets set tight priors. Complex civilization, if it ever existed, must have left durable signals that survived hazard and time, signals that are more likely in the buried record than on exposed plains. Thus, the search strategy shifts from sensational surface scanning towards stratigraphic patience, subsurface radar, targeted drilling into deltaic facies, the examination of anomalous mass and magnetic signals for evidence of concentrated, processed materials. There is an emotional architecture to that enterprise. Whatever the result, discovery, falsification, or extended uncertainty, the process will trigger responses that are as much ethical and existential as they are scientific. If buried artifacts are found, the astonishment would be immediate but not unambiguous. Cultural humility would have to accompany exhilaration. The knowledge that another intelligence once negotiated a planetary trajectory, created artifacts and infrastructures, and then folded into geological memory would reshape human self-perception. It would be a story of kinship across time and an object lesson in fragility. Conversely, if extensive exploration yields no compelling technogenic signatures, the absence itself will educate. It will constrain models of how often complexity escalates to durable material culture and how fragile that culture can be under. Planetary stress. The stakes in either outcome are not merely intellectual. They are operational. The tactics of detection and retrieval are necessarily entangled with questions of contamination and preservation. Planetary protection protocols are not arcane obstacles. They are instruments of fidelity. Forward contamination, inadvertently transporting terrestrial microbes to sensitive Martian archives, could obliterate the biological or chemical signatures that researchers hope to read. Backward contamination, returning alien matter to Earth, could pose unknown biological and societal risks. Those twin possibilities mean that the act of searching is also a moral act. To look without destroying the very record sought requires discipline, investment in sterilization technology, and a governance framework that is global in reach and scrupulous in practice. There is a second set of consequences even more intangible: narrative displacement. Finding evidence of a lost Martian civilization would alter human narratives about uniqueness, origin, and destiny. It would not automatically grant lineage or kinship in a biological sense, but it would show that intelligence has emerged elsewhere in conditions that may overlap partially with Earth's. That revelation would complicate arguments about rarity and contingency in evolution. It would also force a careful interrogation of the human reaction, projection, myth-making, and the appetite for simple, comforting stories. The proper scientific response, patient testing, cross-disciplinary corroboration, and restraint in public communication would likely be at odds with the cultural hunger for immediacy and grand narratives. Managing that disjunction would be a test of both scientific integrity and civil discourse. If the discovery were, instead of non-biological artifacts, slag-like glasses, isotopic anomalies, engineered alloys transformed by time, the interpretive playbook would shift toward materials, science, and stratigraphic context. Laboratories would see cooling histories and vitrified residues, trace element patterns consistent with ore processing, isotopic fractionations incompatible with natural geochemical pathways. The more the pattern coheres, geometry plus chemistry plus stratigraphic singularity, the stronger the inference. But even in such a case, the burden of proof must remain heavy. Planetary processes can mimic, manufacture, impact melts, can glass substrates, hydrothermal systems can concentrate metals, and tectonic processes can produce rectilinear fractures. The difference lies in the number and independence of converging anomalies. All of this makes clear a practical point that is often overlooked in popular imagination. Discovery will not be a single eureka moment captured in a dramatic headline. It will be a slow accretion of evidence, a procession of incremental confirmations and refinements. Public narrative will hunger for crisp answers. The scientific method demands uncertainty, replication, and patient corroboration. That tension is not a deficiency of science, it is the discipline's greatest safeguard against error. If Mars does hold secrets under its sands, their unmasking will be a protracted act of disciplined listening rather than instantaneous revelation. Beyond the immediate epistemic protocol, there is a larger ethical lesson, one that folds back onto Earth. Mars as mirror suggests that human choices now will determine whether humanity itself leaves a record worth reading. The same planetary scale forces that erased habitability on Mars, atmospheric escape, climate thresholds, geochemical sequestration, are instructive about the precariousness of planetary envelopes. Humanity's industrial metabolism alters atmospheric composition, redistributes heat and water, and modifies sedimentary fluxes. If a lesson from Mars is a cautionary tale, it is blunt. Planet-scale processes will patiently rewrite superficial constraints. Leaving a durable legacy, therefore, depends on foresight, intentional design for long-term preservation, investments in archival durability, and governance capable of cooperation across generations. Preservation strategies are both technical and cultural. On the technical side, the most defensible approach to leaving legible testimony is to work with planetary realities. Choose materials and deposition contexts favored by geology. Embed information in highly refractory matrices, glass, ceramics. Certain minerals distribute caches across geologically stable cratons and favor burial at depths that attenuate cosmic radiation and shield from thermal cycling. On the cultural side, the work is about institution building, creating bodies that steward knowledge beyond electoral cycles, that fund long-term archives, and that promulgate norms of intergenerational responsibility. Preservation is not merely a design challenge, it is an ethic to be cultivated. There is a countervailing moral caution. Arrogance about preservation can itself be a form of erasure. The temptation to seed other worlds with human artifacts, the wish to broadcast humanity's presence across interstellar distances, must be tempered by the obligation not to overwrite alien records. Planetary protection is not anthropocentric minimalism, it is a recognition that knowledge is fragile and that the act of looking can be the act of writing. The careful scientist will therefore prioritize non-invasive surveys, sterilization, and the slow path toward invasive sampling. The scenario of Mars hiding civilization under its sands also reframes the search strategies prioritized by funding and politics. If burial is the most likely preservational context, an instrument portfolio should emphasize subsurface penetration, higher frequency radar able to resolve fine layering, drills capable of reaching meters to tens of meters under sterile conditions, sample return architectures that preserve stratigraphic context, and laboratory technologies ready to detect and characterize altered alloys and vitrified thermochemical signatures. The public imagination will clamor for spectacular imagery. Funders and mission designers must reconcile that appetite with the patient, expensive, and meticulous work that will actually move probabilities. There is also a sobering statistical lesson embedded in the mirror. The longer the time scale between a civilization's emergence and the present, the more likely that its artifacts will be degraded beyond recognition. Deep time erases fine-grained complexity with near certainty. Only the most durable, massive, or deeply buried signals stand a chance of survival. Thus, the success of any archaeological search on Mars will be heavily conditioned by chronology. How recently, in geological terms, any hypothetical civilization persisted, and whether it left artifacts at scales and contexts that align with preservation windows. That statistical constraint is not defeatist, it is clarifying. It instructs realistic expectations and motivates technological investments optimized for the narrow domain where survival is plausible. Among the most delicate of ethics is how to communicate uncertainty. The narrative arc of discovery will be shaped as much by public relations as by peer-reviewed papers. The temptation to conflate plausibility with proof is real and dangerous. If Mars yields ambiguous anomalies, intriguing geometric reflectors, unusual isotopic ratios, or vitrified lenses in lacustrine beds, responsible communication must foreground what is known, what is probable, and what remains speculative. The public deserves neither sensationalist promises nor primordialist denials. It deserves a careful translation of probabilities and the steps required to reduce uncertainty. So, finally, the mirror that Mars holds up is reflective in an existential register. The possibility that another technological society might have risen and fallen on a neighboring world thickens the philosophical questions about meaning and contingency. If intelligence is a recurrent planetary phenomenon, then human obligations expand. They include stewardship of fragile biospheres, humility about permanence, and a duty to design institutions that can sustain knowledge across geologic time. If intelligence is rare, then the responsibility is equally weighty. Each example of intelligence is precious, and its preservation, whether through material archives or careful planetary stewardship, becomes a moral imperative. The concluding image is simple and austere rather than cinematic. A rover's drill, patient and sterile, descends into a deltaic lamination. A radar profile reveals an anomaly with rectilinear continuity. Lab instruments slice and probe a sample that bears thermochemical signatures inconsistent with ordinary geology. Steps follow: peer review, interdisciplinary verification, cautious announcements, and the slow work of consensus building. Or nothing of that kind appears, and the red planet keeps its secrets, teaching by absence and tightening priors on what paths complexity commonly takes. Either outcome is instructive. The existence of buried evidence would enlarge the human story and demand new forms of custodial humility. The absence of such evidence would sharpen theories of rarity and fragility and redirect the ethical urgency back toward Earth. In both cases, Mars will have served its richest function as a mirror that refracts human choices into sharper relief. It will have forced an accounting of what it means to leave a legacy and how to sustain intelligible testimony across the deep, indifferent sweep of geological time. The watchers on Earth, scientists, policymakers, citizens, thus face a twin mandate. First, to seek knowledge with instruments calibrated to the planet's likely modes of preservation, and to do so with caution that prioritizes the integrity of any archive encountered. Second, to apply the lessons of planetary fragility at home, to govern with a horizon longer than election cycles, to invest in durability rather than spectacle, to normalize maintenance and stewardship, and to design for entropy rather than denial. If Mars is indeed more than a rust-colored rock, if it is also a mirror and a warning, then the highest achievement of exploration will not be to place a flag, but to return wiser, more careful stewards to a planet that has proven both generous in possibility and ruthless in erasure. The deepest discovery, whether it arrives as an answered question or an increasingly refined null, will be the moral clarity to act in a way that preserves the ledger of human thought for those who read strata and isotopes long after the present breath fades. That, finally, is what the red sands ask, not immediate conquest, but patient attention, not arrogation, but preservation, not a monologue broadcast into the void, but a carefully inscribed and redundantly stored message placed where deep time's hand is least likely to rub it smooth. In that humility lies the truest hope that whatever stories survive on Mars or on Earth will be legible, instructive, and worthy of the species that left them behind.